A single question hangs at the threshold of the solar system. What does an edge look like when viewed not as a line on a map, but as a slow, patient negotiation between light and cold? From a human vantage, edges are abrupt coastlines, borders, the rim of a crater. But the cosmic edge behaves like weather, like a season that takes centuries to arrive. Pluto, occupying that ambiguous boundary, is neither frontier nor void. It is a threshold in the truest sense, a place where the sun's dominion thins to a whisper and the ancient dark history of the system becomes legible in the grain of ice. Pluto sits at the margin, a small world braided into the Kuiper Belt's crowded outskirts. It is not a planet in the classical sense of scale and temper, but it possesses a presence that belies its size. To the instruments of a spacecraft that once brushed past it, Pluto presented itself in high-resolution mosaics of color and texture. To the telescopes that scan its orbit, it is a faint, wandering glint that requires patient observation. This contrast is part of what makes it compelling. Up close, it is richly detailed. From afar, it is persistently elusive. Light that leads the sun takes hours to arrive. For an observer on Earth, morning and night are governed by minutes. For Pluto, a message of illumination is measured in patience. Sunlight there is diluted, sifted through the vastness of space. It arrives as a sallow winter light, pale and patient, imparting just enough energy to coax nitrogen across surfaces, to lift a thin atmosphere into translucence at perihelion, and to allow glacial flows to creep over plains. The idea of sunlight here is almost melancholy, an old, tired theater lamp that has burned around a stage for centuries, still sufficient to reveal silhouettes but no longer to warm. Temperature, where Pluto is concerned, is sculpted by absence. The mean thermal states are measured in tens of kelvins. Molecules that would bind and dance freely on Earth are captured into rigid lattices. Nitrogen and methane freeze into transparent plains. Water ice behaves like rock, and the slightest touch from micro winds can rearrange the surface over generational timescales. The cold is not simply a number, it is a mode of being. It freezes chemistry into long-term memory, preserving in crystalline form a record of the early solar nebula. What on Earth would blur and biodegrade over millennia remains here in arrested stasis, a slow-motion archive. The landscape of Pluto, as revealed by humanity's instruments, carries an unmistakable visual poetry. Vast plains stretch in alabaster sheets, regions where nitrogen and methane settle into a coherent face, interrupted by darker deposits known as tholins, complex organic residues produced by the slow chemistry driven by cosmic rays and faint ultraviolet light. Mountains, jagged and unexpected, rise from these plains, peaks of water ice that behave like basalt. The famous heart-shaped basin, a youthful expanse of smooth terrain, suggests geological processes that are dynamic on timescale short compared with the age of the solar system. Such structures challenge assumptions. How can a place so small and so cold maintain the energy needed? Pluto's orbit is a slow choreography, a long elliptical path that takes roughly 248 Earth years to complete a single revolution. Seasons on Pluto last longer than many human lives. As it travels, its tilt and eccentricity conspire to produce dramatic changes in insolation. At closer approach to the sun, winter's grip loosens and frozen gases sublime into a transient atmosphere. When it recedes, that same atmosphere collapses, condensing back to the ground and blanketing the surface anew. To the planet, time is measured differently. Years are chapters, seasons are epochs, and its surface reads like a palimpsest of these prolonged transitions. In the cold reaches, Pluto is not alone. It exists as part of a populated periphery, a belt of icy bodies, remnants of the protoplanetary disk that failed to accrete into larger planets. These objects range from tiny, inert pebbles to the dwarf planet family that includes Eris and Makemake. Together, they form a dynamic environment, a scatter of histories that can tell a story about the solar system's turbulent youth. Pluto's companionship with its largest satellite, Charon, adds a layer of complexity. They orbit a common center of mass, a binary dance that suggests a violent past, perhaps a collision that reconfigured both bodies and cast fragments into distant paths. The narrative that emerges around Pluto is one of paradoxes. It is small yet geologically surprising, dimly lit yet chemically rich, peripheral yet central to questions about origin and preservation. The outskirts are not merely empty outskirts, they are repositories. In the crystalline ice and in the layers of organics accumulated over billions of years, there is a catalog of primordial materials, a slow ledger of what the early disk once contained. For scientists, these archives are a kind of time capsule. For philosophers of the cosmos, they are a mirror. If the inner planets are loud and messy, the edge is quiet and conservative, holding on to things that time would otherwise erase. That conservatism feeds speculation. In the silence of Pluto's night, the durability of ice raises questions about what can survive the entropy of long durations. Geological features might outlast surface chemistry. Isotopic ratios might record early bombardment. Weak thermal gradients from radioactive decay could permit pockets of internal warmth. The possibility of an internal ocean beneath a shell of water ice is not merely romantic, it is a hypothesis grounded in energy budgets, phase diagrams, and the presence of antifreeze-like components. If such a subsurface pocket exists, it would alter the way one imagines habitability in the outer solar system. It would extend the bounds of environments that can sustain complexity, however sparse, in places previously written off. The human reaction to Pluto, both scientific and cultural, has been charged with narrative. When its planetary status was revised, debates flared not only over taxonomy, but over identity. The story of Pluto has been anthropomorphized in headlines and in popular culture, turned into a tale of demotion and nostalgia. Yet beneath the emotive veneer lies an opportunity to reconsider how classification shapes curiosity. Whether labeled a planet or a dwarf planet does not change the substance of what Pluto can reveal. The object itself remains indifferent to human categories. What matters is that it persists as an artifact of processes that built the solar system. Observation and exploration have their own tempos. For decades, Pluto was a pinpoint of light, a blur in telescopes. The arrival of the New Horizons probe was a singular event in a long trajectory of attention. The images that came back were revelatory not because they altered Pluto's destiny, but because they transformed understanding. In those images, human preconceptions were confronted by real geography, pits, ridges, flowing deposits, and a thin atmosphere that produces stratified hazes. The encounter had the effect of collapsing the distant into the intimate. What had been statistical speculation became vivid terrain. There is a subtle theatricality to the idea of light reaching the edge and being almost entirely stolen by shadow. At the heart of such drama is the interplay between insulation and thermal inertia, between the sun's diminishing push and the inertia of materials that resist change. Shadow, in this context, is not merely the absence of light, but the presence of memory, a state where processes proceed at geological glacial speed. It is where time dilates so that the story of the system is written in frozen syntax. The edge also functions as a laboratory for time. Where erosion is slow and biological activity absent or minimal, surface textures are preserved with a fidelity that permits time-lapse across millennia. The orientation of layers, the distribution of dark tholins, the fractures in water ice mountains, each is a sentence in a text that chronicles solar radiation flux, cosmic ray processing, and volatile migration. For a viewer attuned to deep time, Pluto's surface reads as stratigraphy stitched to orbital eccentricity, a narrative in which episodes of outgassing and deposition recur like phrases in a long poem. Of equal importance is Pluto's role in imaginations that extend beyond empirical science. Speculative meditations that ask what might have been and what could be hidden beneath layers of ice. These thoughts are not reckless fantasy, they are disciplined conjecture, using what is known about physical processes to sketch landscapes of possibility. In a speculative documentary, such hypotheses gain texture, the sense that, beneath the obvious cold, there lurk configurations where chemistry achieves local complexity, where pockets of heat produce running slurries, where ancient impact scars reveal deeply buried material. This is the region where science and wonder meet, where uncertainty is not a void but a space for inquiry. Pluto's existence at the edge compels a rewriting of scale in human perception. Daylight hours measured in fractions of what an earthbound human considers a day, seasons that course over centuries, and geological activity that unfolds at a tempo adjacent to geological time on Earth, all force a reorientation. The edge is a teacher of humility. It demonstrates that not all natural processes obey the rhythms familiar to the biosphere, and that temporality in the cosmos is plural. A mountain on Pluto may be young on an astronomical timeframe yet ancient by human chronology. Conversely, surface patterns might retain traces of events that occurred when life on Earth was in its Cambrian adolescence. This contrast produces a particular emotional texture in any narrative about the outer worlds. There is a sense of smallness. Human history is an ephemeron against the patience of icy bodies. There is temporariness. Labels and categories change, but the bodies themselves continue to record the slow churn of physics. And there is mystery, a suggestion that, even in the meticulously measured, there remain blind spots that invite further exploration. The edge is at once known and unknowable. Instruments can read spectra, map topography, and measure atmospheric pressure. Yet such data open more questions than they close. Why do certain regions appear ancient while others are resurfaced? How does internal energy dissipate within a body? To stand in perspective is to recognize that Pluto's narrative is not an isolated anecdote but a chapter in a larger chronicle about where planets come from and how systems evolve. It is a testament to the complexity that emerges when gravity, radiation, chemistry, and time are allowed to interact without human intervention for billions of years. The outskirts, previously imagined as a dumping ground of leftovers, are instead laboratories of preservation. They are where the system keeps its older drafts, its rough sketches, its initial hand-drawn plans that were later revised as the inner planets cooled, differentiated, and developed atmospheres and oceans. At the same time, the edge is a boundary against which speculation about the past and future plays out. Could such remote bodies harbor clues to prebiotic chemistry? Could remnants of ancient impacts preserve macromolecules in ways impossible to maintain closer to the sun? If civilizations or complex systems leave behind non-biological signatures, dense, durable artifacts, would the cold preserve them better than temperate worlds? These are not claims. They are questions that drag the imagination along a physics-informed path. They insist that the edge be treated not as empty space, but as a potential archive of both matter and memory. As the narrative of Pluto begins here, the journey from light to shadow, it is necessary to hold two lenses at once, the empirical and the speculative, the factual and the philosophical. On one plane, Pluto is a body with measurable geology and atmospherics. On another, it is a metaphor for the margins human thought tends to ignore until instruments demand attention. In both registers, it acts as a counterpoint to immediacy. It asks a viewer to stretch the sense of time, to imagine seasons measured in lifespans rather than hours, and to accept that the edge is not the end, but a palimpsest. Thus, this opening does not intend to answer the edge's central question, but to reframe it. The relevant inquiry is less about defining the boundary and more about understanding what it preserves and what it conceals. From light to shadow, the passage is gradual, punctuated by sublimations and condensations, by seasons that rearrange the face of the planet slowly, inexorably. The story that follows will move along that gradient, exploring how the faintness of light sculpts chemistry, how cold slows decay, and how, in that slowing, the solar system's early stories are encoded. Pluto is a place of edges that invite a sustained gaze. To look at it is to be reminded of smallness and of time's capacity to archive. It is to recognize that the margins of a system can be its most faithful keepers. In the hush beyond the planets, where the sun is a distant lamp and shadow is not merely the absence of warmth, but a repository of history, Pluto remains a patient holder of stories. The rest of the journey will be an attempt to coax them into speech. Imagine a dusk that never ends, a light so thin it seems ceremonial, a faint tawny veil that never brightens into midday and never quite settles into midnight. This is not merely a description of illumination, it is a way to think about belonging. The question that follows is deceptively simple and stubbornly human. Why was the object long taught in classrooms as the solar system's ninth planet removed from that list? The answer is not just a matter of taxonomy, it insists on a different map of the outer system, one in which place and origin provide a context that makes a label feel either apt or misleading. To understand the demotion is to understand where that body was born, and that place is the Kuiper Belt, a vast and crowded periphery that, when the conversation turns to birthplace, the Kuiper Belt demands to be imagined on a scale that leans toward the cinematic and the archival at once. It is a broad, disk-like region beyond Neptune's orbit, populated not by a few isolated wayward stones, but by an enormous census of icy remnants. Billions, perhaps more, of small bodies orbit the sun in a cold, slow ballet. They span the spectrum from meter-sized rubble to dwarf planets hundreds of kilometers across. Some are ruddy and laden with complex organic residues, some are pale, almost bleached, others carry traces of volatile ices that vaporize when they stray inward. The Kuiper Belt is not a neat ring, it is a thick, three-dimensional repository. To place Pluto within this belt is to accept a different logic. For most of human history, the solar system was described by concentric spheres, Mercury to Neptune, and every body within those confined lanes was given a role. But the edge, this crowded outskirts, was never meant to be a single lonely world. Instead, it was a swarm, a community in which dynamical relationships rule. Pluto's orbit is eccentric and inclined. It crosses, it dips into regions closer to the Sun than Neptune, and yet it never collides with Neptune because of a resonance. Pluto occupies a 32 orbital resonance with Neptune, 2 of Pluto's orbits for every 3 of Neptune's, an arrangement that protects it from close approaches. This is not an isolated quirk. A family of objects, the Plutonos, share similar resonances. The Kuiper Belt's existence, and the discovery of its numerous inhabitants, is what forced a rethinking of planetary ontology. For nearly a century after the discovery in 1930 of the ninth object, the classification lingered unchallenged because the catalog of the outer system was sparse. Then telescopes grew sharper, surveys deeper, and in the late 20th and early 21st centuries, astronomers began to find increasingly large bodies beyond Neptune, some as large or larger than Pluto. Two consequences followed. First, the recognition that Pluto is only one among many similarly sized objects. Second, the need to define what planets ought to mean in a system that included a populous belt of comparable masses. In 2006, the International Astronomical Union formalized a definition that introduced three criteria: orbiting the Sun, achieving hydrostatic equilibrium, being rounded by one's own gravity, and clearing the neighborhood around its orbit. It was this last phrase, clearing the neighborhood, that proved decisive. The logic is blunt and, at first glance, technical. A planet must be gravitationally dominant in its orbital zone, having removed or incorporated other debris over the history of the system. Pluto fails this test not because it is small or because it moves oddly, but because it shares its orbital environment with a host of other Kuiper Belt objects. In the logic of dynamical dominance, it is one among a crowd. Thus, it was categorized as a dwarf planet, a designation. This procedural description, however, misses the emotional resonance. The demotion lit a peculiar kind of nostalgia. Popular culture recoiled as if human symbols had been stripped away. The debate revealed something about how labels anchor stories. Children learned 9 planets. That number became psychological scaffolding for human cosmic order. Removing a planet appeared, to many, to be lowering a horizon. But the demotion can also be read as a refinement of curiosity rather than an act of subtraction. It was an invitation to look not at a single entity, but at the context from which that entity arose. Pluto ceased to be a solitary ninth and became, in the most scientifically honest sense, an ambassador for the Kuiper Belt, a gateway to understanding the system. The Kuiper Belt itself is a complex tapestry of dynamical subpopulations. There are the classical Kuiper Belt objects, bodies in relatively circular orbits that have not been strongly perturbed by Neptune. There are resonant populations, like the Plutinos, trapped into orbital commensurabilities that testify to the sweeping migrations of the giant planets in the solar system's youth. There is the scattered disk, where objects have been flung into long, eccentric orbits by gravitational encounters, their fates ranging from quiet isolation to delivery into the inner system as long-period comets. Beyond even these lies the Oort cloud, a diffuse spheroid of icy bodies extending to the Sun's distant influence. Its members are far rarer, but serve as a different the prevailing models of planetary formation and planetary migration, what are sometimes called the nice models, suggest that the early solar system was far less tranquil than its current architecture implies. Giant planets did not form where we find them today, but migrated, scattering the leftover planetesimals and rearranging resonant structures. As Neptune migrated outward, it swept up objects into resonances, sculpting the Kuiper Belt into the structure observed today. In that sense, the belt is not primordial in every detail. It is a palimpsest, overwritten by gravitational encounters that etched new orbits into old material. Yet the materials themselves remain remarkably conservative. The cold preserves chemical structures, ices trap organics, isotopes. Compositionally, Kuiper Belt objects are a gallery of cold chemistry. Water ice forms the structural bedrock of many larger bodies. Frozen nitrogen, methane, carbon monoxide, and other volatiles decorate surfaces, and cosmic irradiation transforms simple molecules into complex, tar-like tholins, which account for the reddish hues of many trans-Neptunian objects. These surfaces record exposure ages and bombardment histories. Cratering, though prolonged and less intense than in the inner system, still pockmarks these bodies, each impact a timestamp. In deeper layers, theoretical considerations and indirect evidence suggest that wherever enough radioactive or tidal heat accumulates, internal differentiation and even subsurface liquid layers could arise. This is why for Pluto in particular, the New Horizons flyby reshaped understanding in dramatic fashion. Its surface exhibited regions of active geology and resurfacing, plains with polygonal cells that suggest convective overturn in volatile ices, mountains of water ice, and a geologically youthful basin, Sputnik Planitia, that hints at internal mobilization of volatiles and perhaps even a subsurface ocean. These discoveries complicated the simple picture of a frigid remnant. Pluto was not merely a cold museum piece, it was a dynamic body with local processes that rearrange its face on timescales that, while geologically long, are not static. Placed in the Kuiper Belt, Pluto's behavior gains meaning. The presence of an atmosphere that collapses and reforms with orbital position, the migration of ices across its surface, the exchange of material with its companion Charon, all of this becomes legible as the habits of a dwarf planet in a populated periphery. Charon itself, large relative to Pluto, speaks to a violent genesis, perhaps a giant impact that left both bodies locked in mutual orbit and reshaped their angular momentum. Such collisional histories are likely typical in dense early belts. They are part of the process that birthed satellites and altered bodies' thermal evolution. Thus, when judged by the criterion of dynamically clearing its neighborhood, Pluto's inability to there is a deeper, more speculative thread that runs through the notion of the Kuiper Belt as both birthplace and archive. Cold, distant, and shielded from sunlight's erosive intensity, Kuiper objects can preserve brittle records for billion-year timescales. Complex organics synthesized by ultraviolet irradiation and cosmic rays accumulate as stable residues. Traces of early solar system chemistry, volatile inventories, isotopic fingerprints are less likely to be erased than they would be within the thermal churn of the inner planets. If one seeks the solar system's childhood drawings, many of them are folded into the belt's inventory. Comets that swing inward and reveal pristine interiors are samples of that residue. This preservation gives rise to a tempting and disciplined speculation about deep-time archives. If the outer system is where material endures, then it is also where certain kinds of signatures, macroscopic artifacts, unusual mineral assemblages, or anchored chemical anomalies would survive longest. That thought has practical implications for how humanity imagines searching for ancient markers of processes no longer active. It reframes the Kuiper Belt not only as a laboratory for planetary science, but as an archive for the system's broader history. In that archive, the distinction between being a planet and being a dwarf planet is less consequential than the preservation and transmission of information across immense spans of time. The debate around Pluto's status, therefore, encapsulates multiple tensions. There is the desire for tidy categories, the pedagogical utility of memorable lists. There is the scientific requirement for definitions that reflect dynamical realities. And there is a cultural response to reclassification that betrays how much humans invest identity into cosmic order. But push beyond the headlines, and one finds a different moral. Identity in the cosmos is contextual. A mass of rock and ice may be a planet in some senses and a member of a larger set in others. Its significance arises not from a one-word label, but from what it reveals about origins, evolution, and preservation. To stand back and view the Kuiper Belt as Pluto's nursery is to accept a humility before scale. A body that once symbolized the furthest mainstream planet is now a representative sample of a populous frontier. Its valence changed. It went from being an endpoint to being an index. The shift did not diminish its scientific worth. If anything, it expanded the narrative. Pluto's story became a doorway into a broader inquiry about how the solar system's outskirts behave, how cold chemistry proceeds, how weak sunlight moderates volatile cycles, how minor bodies carry the signatures of formative events. The belt's billions of denizens also remind observers that the solar system is not a simple collection of lone worlds, but an ecosystem of orbits and resonances. Gravitational influences reach out across tens of astronomical units. Migrations of giant planets can reconfigure entire populations. Small impacts and slow thermal processes continue to sculpt even the most distant objects. The Kuiper Belt is therefore not a static belt of relics, but a slow-moving organism of dynamical memory. In the end, the question of why the former ninth planet was removed from the planetary list is answered on two levels. Practically, the demotion followed from an operational decision about what counts as a planet in a crowded, differentiated system. Philosophically, it reflected a maturing of human perspective, an acceptance that place, origin, and dynamical context matter. Understanding Pluto demands understanding the Kuiper Belt, the cradle that made it, the crowd that shared its orbit, and the preservationist cold that allowed it to maintain a visible record of early solar history. The image of an eternal dusk returns here as metaphor and mechanism. In the dim reaches where sunlight is weak and seasons drag across centuries, the Kuiper Belt acts like a slow conservator. It keeps things from the turmoil of inner places, it remembers chemical recipes and orbital legacies. Pluto, once mistakenly thought to be an isolated ninth, is thus better read as a conversation partner in a crowded room, a voice among many telling parts of a larger story. The label dwarf planet may feel diminished in trivial lists, but within the architecture of the solar system, it is a precise recognition, a way of saying that the outer system is a different kind of neighborhood, one in which being a rounded, self-gravitating body does not confer exclusive. That role, in turn, opens the narrative outward. The Kuiper Belt is not merely the scene where demotion was decided, it is the place that reframes the significance of bodies that live there. It invites questions about how remnants preserve the past, and about which places are most likely to carry legible traces across deep time. In the next movement of the story, the focus will narrow again, from the belt to selected bodies within it, probing how individual surfaces and subsurfaces keep records, and how the faint, everlasting dusk shapes the chemistry and geology of these distant objects. For now, the lesson is clear. To name is to categorize, but to understand is to place. Pluto's reclassification is less an erasure than a recruitment into a great, cold archive whose billions of inhabitants together. What does preservation look like when the first breath of the sun barely warms a body at the edge of its system? The question is at once geological and poetic. Locked into the chemistry of ice is a record that stretches back to the very birth of the solar system. Pluto, like its siblings in the distant belt, is not merely a little world, it is a fossil of process. a frozen ledger written at the moment when gas and dust cohered into rocks and ices some 4.6 billion years ago. In the long narrative of planetary formation, the outskirts tell a simple origin story told in slow motion. The protoplanetary disk that birthed the Sun was a turbulent, temperature-stratified sheet of material. Close to the star, heat vaporized volatiles. Far from it, temperatures plunged and gases condensed into solid grains. There, beyond the frost line, microscopic grains of water ice, ammonia, methane, nitrogen, and carbon monoxide grew sticky, aggregating into pebbles, then clumps, then kilometer-scale planetesimals. Under the weak, cumulative influence of gravity and the random shoves of collisions, these aggregates accreted into larger bodies. In the light of modern cosmochemistry, the storyline is measured. The ice, in this context, is not an inert coat. It is structural, energetic, and archival. Water ice forms a rigid skeleton, supporting topography and mountains. More volatile ices. Nitrogen, carbon monoxide, methane function as mobile agents, sublimating and freezing with changes in insulation and orbital position. Within the grain of an icy body, chemistry and physics conspire to preserve a memory that continental drift or hydrological cycles on an inner world would obliterate. Cosmic rays and faint ultraviolet light slowly alter surface molecules, turning simple organics into complex macromolecular residues. Tholins that redden surfaces and record exposure histories. Isotopic ratios of nitrogen, argon, and xenon remain legible, providing clues to the provenance. Denser and siblings sharpen the sense of diversity within the Kuiper belt. Eris, for example, is an object of comparable size that once upset human assumptions by challenging Pluto's uniqueness. Denser and more massive in certain estimates, Eris carries a brighter, more reflective surface, suggesting a fresher coating of volatile ices or recent resurfacing. Makemake and Haumea present contrasting tales. Makemake wears a reddened surface, while Haumea's rapid rotation and elongated shape betray a violent past, perhaps a disruptive collision that ejected fragments and sculpted its ring and moons. Sedna and the distant, highly eccentric objects linger even farther out, their orbits hinting at past disturbances, interactions with migrating giant planets, or perhaps the ghost of an unseen perturbing mass. Charon, Pluto's the origin story accretion of ice and rock about 4.6 billion years ago carries consequences beyond composition. Bodies formed at the margin may differentiate if interior heat is sufficient, heavier silicates sink, lighter ices float, and chemical gradients develop. Radioactive decay of short-lived isotopes early in the solar system could have supplied enough internal warmth for partial melting and differentiation in some objects. Even in the distant present, residual heat augmented by tidal interactions in binary systems can maintain subsurface layers warm enough for sluggish, slushy dynamics. Ammonia, acting as an antifreeze, lowers the melting point of water and creates the possibility of long-lived subsurface reservoirs in smaller bodies than would otherwise be possible. Thus, understanding Pluto alongside his companions requires attention to the long, elliptical route it takes around the Sun. Its orbital journey is not a static circle, but a slow, pensive arc through an environment where sunlight is a thin, patient visitor. Pluto's orbit is notably eccentric and inclined. It swings from about 29.7 astronomical units at perihelion to roughly 49.3 AU at aphelion, tracing a path that takes approximately 248 Earth years to complete. This elongated orbit shifts solar input dramatically over the course of a single Plutonian year. When near perihelion, sunlight, though still faint compared to Earth, becomes sufficient to sublimate nitrogen and methane ices, puffing up a transient atmosphere and mobilizing volatile cycles across the surface. As Pluto The pace of these seasonal changes introduces a scale of temporality that challenges human intuition. Seasons, measured in decades and centuries, stretch like winter on a polar world that does not know an easy spring. The atmosphere's waxing and waning modulates surface processes over timescales that outlast many human institutions. It writes patterns in long freezes and slow migrations. Volatile transport is not the rapid, windswept redistribution familiar on Earth, but a glacial, sublimation-driven pilgrimage. Regions can act as cold traps, places where volatiles accumulate preferentially across orbital cycles. Sputnik Planitia, the vast heart-shaped basin identified by New Horizons, functions as such a trap. Its depression, Pluto's resonance with Neptune, the 3002 mean motion resonance, adds another layer of temporal governance. It is a dynamical choreography that prevents collision despite orbital crossing. For every 3 orbits Neptune makes, Pluto completes 2. This resonant protection is a fossil of the solar system's tumultuous adolescent years, when giant planets migrated and swept smaller bodies into gravitational grooves. The resonance also places Pluto among a larger class of Plutonos, objects that share this orbital rhythm and thus share a common dynamical heritage. As a population, these objects are signposts of migration. Their distribution and properties encode the history of how the outer planets rearranged the solar system's architecture. Comparative geology across trans-Neptunian objects is still an emerging field, but where data exist, the contrasts are illuminating. Surfaces vary from bright, reflective expanses of volatile ice to ancient, tholin-darkened terrains. Cratering records differ. Some regions appear heavily pummeled, preserving the slow rain of impacts over eons. Others look surprisingly young, reshaped by tectonics, cryovolcanism, or volatile flows. Cryovolcanic features, where subsurface slurries of water, ammonia, or briny mixtures may have erupted and refrozen, offer routes for chemical renewal and redistribution. The presence of mountainous ranges on Pluto composed of water ice underscores the mechanical strength of frozen water. At such frigid temperatures, ice behaves not as a brittle glaze, isotopic fingerprints deepen the comparative picture. Ratios of nitrogen and carbon isotopes point to differences in volatile source regions and processing histories. If, for instance, an object shows an excess of a rare isotope, it may indicate accretion of a different reservoir of material or a processing pathway dominated by irradiation or fractionation. Such signals, when read across multiple bodies, can map gradients in the protoplanetary disk narratives of where materials condensed and how they migrated. Beyond the immediate physical properties, the outskirts raise grander epistemic questions about permanence and archival capacity. Coal preserves structure, and structure preserves information. Where inner planets recycle their surfaces through plate tectonics, erosion, and biology, trans-Neptunian objects collect and hold. Macrostructures impact basins, accretionary layers, trapped volatiles remain legible for far longer. This suggests that, for anyone seeking the solar system's earliest recipes, the Kuiper Belt and scattered disk are promising canvases. Comets that visit the inner system are, in a sense, sampling agents, peeling back layers and exposing primordial mixtures that otherwise would remain hidden behind a curtain of distance. Speculation, if bounded by physical plausibility, acquires rigor in this context. The idea that certain forms of complex chemistry or even long dormant microenvironments could be preserved under an ice cap is not mere fantasy. It is an extrapolation from known thermodynamics, phase behavior, and the demonstrated chemical resilience of organics at low temperatures. The possibility of subsurface brines or pockets warmed by radiogenic heat and perhaps punctuated by episodic cryovolcanic exchange creates niches where molecular complexity can persist or be transiently active. Such pockets would be tiny in spatial extent and slow in kinetics, but they would be significant as examples of how habitability is a spectrum rather than a binary declaration. Yet the allure of preservation extends beyond chemistry to a more provocative conjecture. What kinds of information best survive cold, dark places? Material durability favors refractory minerals, metal artifacts, and crystalline structures that withstand radiation without facile degradation. Macromolecules, polymers, aromatic-rich organics can persist as tar-like residues. The slow, methodical accumulation of irradiation by cosmic rays will alter surfaces, but will also lock them into new chemical steady states that encode exposure. If artifacts of non-natural origin were ever placed on such worlds, the odds of their persistence are higher in the periphery than in the geologically active inner system. This is not an argument for anything definitive. Rather, instrumental glimpses have already transformed speculative ideas into constrained knowledge. New Horizons' reconnaissance of Pluto was a singular event that departed from telescopic indirection and offered proximate detail. The spacecraft revealed young surfaces, evidence of volatile convection, and atmospheric hazes, data that reshaped models of what small, cold bodies can do. Ground and space-based telescopes complement such flybys by tracking long-term variability, mapping spectra, and identifying new members of the distant population. Each dataset refines the comparative framework and narrows the plausible narratives about formation, evolution, and preservation. The longer arc of human curiosity is itself a season of learning. Initial anthropocentric narratives gave Pluto a simple role, the ninth planet, an endpoint. The subsequent reframing placing Pluto among a populous belt and tracing origins to a 4.6 billion-year-old accretion from ice and rock honors complexity over simplicity. It recognizes that the marginal zones are not deserts but crowded repositories that conserve early conditions. It also insists on a scale of patience, the movements of volatiles, the slow growth of organic tholins, the sedimentation and sublimation cycles all take place on timescales that make human lifetimes blink-like. What remains, when the telescopes are stowed and the spacecraft move on, is the sense of deep time encoded in ice. A simple sheet of nitrogen on a distant plane is at once a chemical compound and a parchment of cosmological memory. Comparison across sibling bodies reveals variations in composition, collisional history, and orbital fate, each a stanza in the system's origin poem. The long elliptical journey around the sun, marked by resonance, eccentricity, and the languid choreography of seasons, operates as a clock that reads not in hours but in centuries. In that temporal register, processes that seem immaterial to human urgency are the key drivers of form. In the quiet of the Kuiper Belt, preservation and change coexist. Ice conserves, orbital mechanics agitates. Sublimation erases and redeposits, impacts punctuate continuity. Through these mechanisms, the outskirts safeguard the solar system's early experiments, offering a library of materials that, with careful reading, can tell where the system began and how it rearranged itself. To approach Pluto and its kin as archives is to adopt a humility, to understand that the most telling records are often those that endure not because they are dynamic, but because they resist the haste of turnover. The cold is not mere absence of warmth. It is a conservator's slow hand holding the earliest pages of a cosmic book, waiting for readers' patient. What does it feel like to stand, in the imagination, on a surface where cold is not an absence but a sculptor? Which kinds of landscapes are made when sunlight is a whisper and ice behaves like stone? These are not purely geological inquiries, they are invitations to rescale the senses. On Pluto, the visible surface is an archive of slow processes, an art gallery where season and chemistry hang side by side and where the very notion of erosion moves at a tempo almost inimical to human impatience. To describe that terrain is to read the handwriting of deep time in a language of frost and shadow. At the center of that handwriting lies Sputnik Planitia, the pale, heart-shaped plain that arrests every eye that has ever looked at Pluto closely. From a distance, it appears as a calm, alabaster basin, serene, almost domestic in outline. Up close, the plain resolves into a mosaic of polygonal cells, their edges delineated by faint ridges and troughs. These are not crystalline facets of a mineral but convection cells in a sea of nitrogen ice. In conditions where temperatures are measured in tens of kelvins, nitrogen behaves more like syrup than like the brittle frost one might imagine. Warmed very slightly by sunlight and perhaps by internal heat, the slab begins to flow. The slow overturn of material within those polygons is a geological heartbeat at a. The texture of Sputnik Planitia suggests a paradox: youth betrayed by cold. The surface shows remarkably few impact craters, implying that it has been resurfaced relatively recently in the history of the solar system. How does a marginal world, isolated and dim, find ways to erase the pockmarks of time? The answer is partly mechanical and partly climatic. Nitrogen ice is more mobile than the heavier water ice that forms Pluto's mountains. It sublimates and recondenses as Pluto's seasonality alters the local balance of sunlight and shadow. Ice is transported, pooled into low basins, blown in micro winds, and convected from beneath as warmer material resurfaces. These combined processes can flatten and refresh terrains on scales appreciable. That plain is not a uniform sheet. Around it, there are borders, rims where plains give way to rougher terrain, scarred by tectonic fractures and piled with the debris of past upheavals. Mountains rise abruptly, not as hummocks of frozen snow, but as true ranges, towering edifices of water ice, their faces jagged and steep. At Pluto's temperatures, water ice is as rigid as basalt. It is a bedrock on which lighter, more volatile ices can rest. The peaks of the Tenzing and Hilary Montes pierce the nitrogen sea like frozen steeples, their flanks pocked by terraces and fault scarps that hint at collisions, uplift, and the slow collapse of slopes under their own weight. The sight of such relief on a world smaller than Earth's moon is a reminder that edges are always interesting places. Along the margins of Sputnik Planitia, the interaction of water-ice mountains and mobile nitrogen plains produces dramatic boundary phenomena. Blocks of water ice, some angular, others rounded by slow attrition, appear stranded in the nitrogen plain, like boulders on a coastal shelf left behind by a retreating sea. Their bases may be overlain by sediments of darker tholin material, colored by the slow chemistry of cosmic irradiation. Where the plain shuts against uplands, sharp scarps and cliff faces create microclimates. Preferential deposition of frost on downwind faces, differential sublimation that etches small cantilevered overhangs, and the intermittent exposure of older, darker layers beneath the fresh nitrogen. Beyond Sputnik's white hush, the surface language diversifies. There are regions of dark, rust-colored plains, Cthulhu Regio among the most prominent, where tholins dominate and where the record of irradiation is plainly visible. Those dark streaks act like a varnish, a slow, tar-like accumulation that preserves older surfaces from the bleaching effect of fresh, volatile deposition. The contrast between dark and light regions is not merely cosmetic. Albedo differences create feedback loops. Bright areas reflect what little sunlight there is, staying colder and thereby trapping volatiles. Darker patches absorb more light, warm fractionally, and permit different local chemistry. Over successive long seasons, these small differences can magnify. Another striking terrain type on Pluto is the bladed, serrated topography of what has been termed Tartarus dorsa. From a distance, these appear as fields of razor-like ridges, long, thin blades of methane ice that climb into an almost alien skyline. How such features form is a question that blends microphysics with climatology. One plausible pathway involves sublimation-driven erosion, layers of methane ice, deposited slowly over time, are sculpted by preferential vaporization along fractures and by the directional influence of sunlight at low solar angles. The resulting ridges are persistent because, at those low temperatures, the base material is strong. Bladed terrain is a reminder that Pluto's climatic mechanisms can produce. Pluto's mountains are not all born of the same process. Some suggest tectonic uplift, others implicate cryovolcanic activity. Wright Mons and Pickard Mons, for instance, stand as gently domed edifices with deep central depressions, morphologies that invite interpretation as cryovolcanoes, places where slushy mixtures of water, ammonia, and volatiles might have once erupted and cooled into resistant edifices. Cryovolcanism, if it occurred, would be an episodic process, perhaps sparked by internal heating or the buoyancy of briny mixtures. The very possibility complicates a naive image of a dead, frozen world beneath a rigid crust. There may be places where chemistry and pressure drove eruptions, altering the surface and the basin structure of Sputnik Planitia itself argues for a dramatic origin. Its circular boundary and the concentration of low-lying, bright nitrogen ice suggest that it is an impact basin, one large enough to have depressed the crust and created a gravitational sink. Such a depression would naturally capture volatiles, creating the conditions for long-term sequestration. There is an additional, subtle consequence. Mass anomalies like this can torque a planet's orientation. In Pluto's case, the redistribution of mass towards Sputnik might have induced reorientation of the body, true polar wander, bringing that basin toward an equatorial or polar alignment over geologic time. This interplay of impact mechanics, mass transport, and reorientation is the sort of narrative that the thin atmosphere above all these features deserves attention. At closest approach to the sun, faint though it is, sunlight sublimates nitrogen and methane, lifting molecules off the surface into a tenuous envelope. Pressure peaks at only a few microbars, less than 100,000th of Earth's atmospheric pressure, but it is enough to sustain layered hazes and to permit gas phase chemistry that modifies surface molecules. At greater distances, the atmosphere collapses, gases condense and fall again, blanketing regions in frost. Those cycles translate into surface mobility. Volatiles cross planes and gather in basins, haze particles settle and darken terrain, micro winds, channelized by topography, redistribute light sediment. In effect, the entire atmosphere is a seasonal. Textures on Pluto's surface record these atmospheric interactions. Fine streaks indicate wind-directed transport. Pits appear where sublimation preferentially removes material. Polygonal cracks betray the stress history of underlying layers. Even glacial-like flow features can be observed. Tongues of nitrogen ice pushing into lower-lying areas, their margins smooth where flow is continuous and ragged where movement stalls. It is tempting to anthropomorphize these flows as familiar ice sheets, but the proper caution is to appreciate the analogies without losing sight of different physics. The dominant mobile material is nitrogen, not water, and its rheology at these temperatures changes the character of flow. The chemistry of Pluto's surface is both simple and deeply complex. Simple in the sense that the dominant players, nitrogen, methane, carbon monoxide, and water, are molecules that terrestrial chemists know well. Complex in the sense that, under the irradiation of ultraviolet light and cosmic rays, those simple molecules undergo slow alchemy, knitting into longer chains and complex macromolecules. Tholins, the terry byproducts of such processing, stain the landscape in red-brown hues and are a visual testament to the patient work of radiation. Their formation is slow, their accumulation measurable across eons, and their presence alters the surface's optical and thermal properties. In other words, chemistry here is an agent of both color and there is an emotional atmosphere to these plains and peaks as well, an effective texture the narrator cannot avoid. Observing Sputnik Planitia is like listening to a choir in which every voice is drawn out over centuries. Each polygonal cell, each blade of methane, each scarred mountainside is a long note. The tempo is gentle but inexorable. The experience invites a recognition of minuteness. Human epics are flashes against these slow processes. Yet the emotive response is not only humility. There is also an austere beauty in the restraint of the landscape. Where Earth's geology can be dramatic and noisy, rivers carving canyons, tectonics shoving mountains skyward, Pluto's dramas are quiet, their gestures slow and precise. Speculative thought finds fertile ground here. If parts of the surface are actively recycling volatiles and, perhaps occasionally, exposing deeper material through cryovolcanic vents or troughs, then these places become portals to older reservoirs. Each convected polygon might bring to the surface molecules that were entombed epochs ago. Each cryovolcanic edifice could be a natural sample return, delivering a paste of subsurface materials to the exterior. For a planetary scientist, this is intoxicating. The near surface becomes a palimpsest, where earlier pages are periodically exposed to the thin atmosphere and faint sunlight, allowing for direct observation of primordial chemistry without the complete obliteration that inner planets inflict on their surfaces. The interdependence of features is worth pausing over. Mountains shape wind, planes modulate deposition, albedo influences temperature, impacts create basins that trap volatiles, which in turn change the mass distribution and the planet's orientation. The system is not a set of isolated parts, but an orchestra of slow processes that influence one another. The heart-shaped basin, the water ice peaks, the bladed ridges, the hazes above all, are actors in a choreography dictated by low gravity, weak sunlight, cold chemistry, and the inexorable march of deep time. And then there is the most reflective question. What is preserved here that nowhere else can hold so faithfully? The answer returns to the core thesis of preservation. The cold and the slow mean that many kinds of information, chemical signatures, impact histories, and even structural arrangements remain legible across time spans that would be unthinkable on Earth. The plains of Sputnik Planitia are thus both a book and a conservatory. They keep records with a patience that only the margins of a system can afford. For those who come with instruments and models, Pluto's surface is not merely a destination but a methodology. Read the frost, and read it patiently, and the story of the solar system's infancy starts to unfold. In the end, the surface of Pluto is a lesson in scale and subtlety. Its beauty is cold, precise, and unostentatious. Its dynamics are patient and stubborn. It does not shout, it preserves. Those who listen to its slow autobiography are rewarded not with immediate revelation, but with a deepening comprehension of how time, cold, and chemistry conspire to keep the oldest pages of a solar system legible. The frozen plain, the jagged peaks, the serrated ridges, the faint atmosphere, each element contributes a stanza to a poem that spans billions of years. To read it requires recalibration, an acceptance that geological liveliness can be gentle, that youth can be preserved in frost, and that the edge of a system is often its most faithful archivist. What does it mean for a world to breathe at the edge of a system where light arrives like a shy visitor? The image is simple and strange, a faint exhalation of gas that swells into being as a planet draws nearer to its star, then collapses back into ice as the long winter returns. For Pluto, this rhythm is not metaphor alone, but the governing fact of its present-day climate. Its atmosphere is not permanent in the way an earthly atmosphere is. It is seasonal, intermittent, a veil that appears and vanishes on orbital timescales measured in decades and centuries. That breath, so thin, so transient, is central to understanding how the surface is painted, how heat moves, and how memory is at typical temperatures near 40 to 50 Kelvin, an average often rounded to about minus 20-30 degrees Celsius. Pluto's chemistry in the warm, aqueous sense. Nitrogen, methane, and carbon monoxide are not trace curiosities on the surface. They are the principal actors. Where those volatiles have accumulated, the surface takes on a characteristic palette: the pale, reflective expanses of nitrogen ice, the bluer sheen of methane deposits, and subtle spectral fingerprints of carbon monoxide. These materials both shape appearance and animate behavior. Nitrogen, the most volatile of the three, is the workhorse of Pluto's atmosphere. At perihelion, it sublimates from frost into gas, populating a tenuous envelope that can reach hundreds of kilometers above the surface. Methane and the atmosphere's height and thinness are worth imagining in parallel. From a spacecraft's perspective, it is unexpectedly extensive. Hazes and tenuous gas layers stretch upward, scattering sunlight far above the ground. From a pressure standpoint, it is almost laughably rarefied, measured in microbars, a whisper next to Earth's robust air. Yet those microbars are enough to sculpt the surface over long durations. They lift particles, drive slow winds, enable the transport of volatiles across long distances, and seed the skies with hazes that, when they fall, alter the ground. The very existence of such a transient envelope creates a climate system that cycles matter between atmosphere and surface. The appearance and disappearance of this atmosphere are governed by orbital geometry and thermal inertia. Pluto's orbit is markedly eccentric. Perihelion brings it significantly closer to the Sun than aphelion, and over the course of a 248-year Plutonian year, the flux of sunlight changes sufficiently to drive sublimation or freezing of volatile ices. But the process is not instantaneous. Ice does not vaporize or condense on a whim. Layers of frost, subsurface thermal inertia, and the buffering influence of topography introduce lags, hysteresis, and regional variation. Consequently, an atmosphere can outlast a close approach. It can persist for decades even as the planet continues its slow retreat. Conversely, as heat drains away, the air collapses, gases. These Sphetos subtleties lie. At low solar incidence, nitrogen ice is bound to the ground. As sunlight increases, it sublimates, creating pressure that supports layering and hazes. These hazes do more than scatter light. They are chemical phaetres. UV photons, fed by sunlight and catalyzed by energetic particles from the solar wind and cosmic rays, break simple molecules apart. Freed radicals recombine into longer chains and aromatic systems, molecules collectively known as tholins when they polymerize into complex tar-like substances. Much of the red-brown coloration noticed across Pluto's darker terrains, areas of Cthulhu Regio and other rust-colored plains, is a consequence of these processes. Some tholin formation happens at the surface under direct irradiation. Much of it is produced aloft in the atmosphere. That feedback is not merely cosmetic. Albedo differences between bright nitrogen-rich plains and darker tholin-laden areas create thermal contrasts. Bright regions reflect a larger fraction of the meager sunlight and therefore stay colder, acting as cold traps that preferentially capture volatile gases. Darker areas absorb relatively more heat and can become local warm spots where sublimation is favored. Over many orbits, these local differences become exaggerated, creating landscape-scale heterogeneity. Sputnik Planitia, the vast, pale, heart-shaped basin that commands attention in every high-resolution image, functions as such a cold trap. It collects nitrogen preferentially, sustaining a reservoir that can modulate not only local climate but global angular momentum. The accumulation of mass in a basin can shift the atmosphere's ephemeral nature complicates chemical pathways. When a gaseous envelope is present, molecules are available for gas phase reactions, and transport species released from one latitudinal band can be carried by winds and redeposited elsewhere. Without that envelope, surface chemistry is dominated by direct irradiation and slow, immobile processes. The alternation between these regimes over centuries creates layered histories and frost strata of deposition that preserve snapshots of past climates. A scientist reading those strata is not unlike a person holding rings of a tree, each layer a season, each compound a year in which certain conditions prevailed. Over millions or billions of years, these cycles accumulate a palimpsest whose pages are written in the language of volatiles and radiations. Despite its faintness, the atmosphere is not passive against external forces. Solar wind and charged particles can strip the upper layers because the gravitational well of a small body like Pluto is shallow and thermal speeds of lighter molecules can exceed escape velocities. The result is a slow leakage. Molecules that are lofted to high altitudes may be accelerated and flow outward into space. During periods of higher solar activity, enhanced particle streams can increase escape rates, while at other times the process is quieter. New Horizons measured such interactions. The solar wind carves a tail, ions are picked up and carried away, and the exosphere merges into the streaming plasma. Atmospheric escape is not catastrophic on immediate timescales. That potential for replenishment raises another speculative and scientifically grounded consideration. Beneath Pluto's frozen crust, pockets of slushy material may survive, warmed either by the decay of radioactive elements or by tidal interactions forged in its complex dance with Charon. If subsurface layers contain antifreeze compounds, ammonia being the natural candidate, or brines with dissolved salts, melting points drop and liquid phases can persist longer than pure water would allow. Cryovolcanism becomes a plausible mechanism to resupply the surface and atmosphere with volatiles. When a subsurface pocket finds a conduit to the surface, it can erupt slurries that refreeze as lobate deposits and deposit fresh ices atop older layers. Those events, perhaps rare, punctuate the Observationally, the intermittent nature of Pluto's atmosphere has already been documented in subtle ways. Stellar occultations, moments when Pluto passes in front of a distant star, reveal the existence and density of the atmosphere by the manner in which starlight dims and refracts. Decades of such observations show variability in pressure, a signal that atmosphere is not static. Spacecraft encounters add texture. The layered hazes recorded by instruments, with structures extending tens to hundreds of kilometers above the ground, surprised many researchers because they indicated more complex aerosol formation than a simple tenuous envelope would suggest. These layers are stratified, with optical properties that vary with altitude: denser, scattering hazes that produce a twilight glow above the horizon, thinner upper strata that interact with solar wind. Observers infer the emotional tenor of these discoveries is subtle but pervasive. The intermittent atmosphere invites a kind of narrative humility. Pluto's climate refuses to be stereotyped. It is not a frozen museum sealed once and for all. It is a place of cycling states, of visible and invisible phases. To the human capacity for wonder, that cyclicality is both melancholic and consoling. It evokes images of breath, temporary, necessary, intimate. There is an aesthetic sense to a world that does not hold on to atmosphere forever, a quiet drama enacted not in explosions but in the patient choreography of phase change and light. There is also a caution in this drama. The presence of an atmosphere, even a seasonally ephemeral one, accelerates some forms of surface change and retards others. It can smooth out small impact scars by transporting and depositing ice across basins. It can facilitate the formation of organic veneers that hide deeper material. It can periodically expose subsurface chemistry through cryovolcanic upwellings or by scouring induced by micro-winds. The intermittent nature of the envelope therefore complicates the planet's role as an archive. Some episodes favor preservation, cold sequesters, frost berries, and others favor exposure and alteration. The net result is a record that is richer and more complex than either an utterly inert or a perpetually active search. Linking the atmosphere's behavior back to broader narratives of the solar system's outskirts deepens its significance. The long seasons that enable atmospheric collapse and rebirth are comparable to human histories in scale. A single Plutonian season can last longer than a human life. These slow cycles are a lesson in patience, both in literal time and in the epistemic patience needed to understand processes that unfold across centuries. When the Sun draws a little closer and Pluto breathes out a thin atmosphere, it does so within a temporal architecture that resists instantaneous interpretation. Observers must collect evidence across many returns, across generations of instruments, to compile a convincing chronology. Finally, the intermittent atmosphere is an emblem for the larger theme of margins preserving memory. Where inner planets churn and recycle, the outskirts oscillate between exposure and sequestration. The episodic presence of an atmosphere does not erase the function of preservation, it refines it. Volatile cycles can bury and uncover material, hazes can paint surfaces with chemical records produced aloft, and slow winds can transport signatures across hemispheres. In the cold, the planet is both archivist and editor, preserving fragments of the ancient protoplanetary mixture while selectively rewriting its outermost pages through seasonal breath. Pluto's breath, so faint, so temporary, maps a moral for how the solar system keeps and discards memory. The atmosphere appears like a submerged city briefly revealed at low tide. Structures become visible, sediments rearrange, and then the tide retreats, entombing what was exposed. To study that city requires a patience that mirrors its own slow breathing. To listen to Pluto is to tune one's sense of time to cycles barely perceptible in a single human life. In that tuning, the intermittent atmosphere becomes not only a physical curiosity, but a metaphor for attentive inquiry. The edge of a system does not simply hold on to the past by freezing it. It breathes, occasionally bringing the past into the light and then folding it away again. What does it mean to discover the outskirts of a system not by a sudden, bright flare, but by a patient accumulation of difference? By noticing what does not belong because it moves against the fixed pattern of stars. That question is at the heart of an event in 1930 that, for a brief and gleaming moment, expanded the boundary of what people imagined to be the solar system. The discovery of Pluto was not a thunderclap. It was a slow, meticulous act of subtraction, plate after plate, night after night, until a tiny point of light betrayed a motion that belonged to the sun's company rather than to the firmament's indifferent backdrop. The search that culminated in that discovery was itself an expression of a particular human temperament, a willingness to trade immediate spectacle for the long rewards of discipline. In the early decades of the 20th century, telescopes and photographic techniques had advanced to the point where the sky could be catalogued systematically. Astronomers began to lay down strips of the heavens on glass, two exposures separated by days or weeks, and then to compare them eclipsingly, looking for objects that shifted. The instrument that made the comparison possible, the blink comparator, was a simple, percussive tool of modern patience. It allowed the eye to see movement where the unaided glance perceived only a tapestry. Against that slow, mechanical rhythm, a single human being. To speak of the discovery is to speak of context, the late Percival Lowell's geometries of a missing mass, the public appetite for a ninth planet, the telescopic surveys that sought to vindicate an idea about gravitational perturbations in Neptune's wake. It is to speak of a particular observatory perched under a dark prairie sky and of the methodical work of examination. The name linked to the moment. Clyde Tombaugh belongs to a young amateur astronomer given the task of executing precise, repetitive comparisons. He was not a mythic figure storming the void. He was an observer, a technician of attention. The discovery did not arrive by inspiration alone, but by the slow choreography of labor and instrument. On a February night in 1930, two photographic plates, exposed weeks apart, were brought to the blink comparator and set to the ritual of alternation. The mind relaxed into the mechanical flicker. Most of what moved, the satellites of the planets, known asteroids, had familiar signatures. And then there was a movement that did not belong, a point of light shifting in a manner consistent with a body orbiting the sun at a vast distance. That subtle motion, when confirmed and followed up, was the birth of a new entry in the catalog of solar companions. The immediate response among astronomers was nearly electrical in tone. The nomination of a new body triggered professional curiosity and public fascination at once. In the weeks that followed the announcement, telegrams and letters circulated, observatories pointed radios and refractors at positions on the sky to confirm the finding. The idea of a ninth planet was arresting because it extended the human mental map outward. Newspapers treated the discovery like the opening of a frontier. Here was an endpoint to the planetary order that had seemed immutable. The name chosen. Pluto arrived by a small and humane route, a suggestion from an 11-year-old in England that threaded classical imagery with the whimsical sense that a distant, dark world should be named for the other. Yet the first impression of a new planet of large, elemental significance was provisional. Early telescopic measures overestimated what little could be measured at such distance. The object's flux was faint, its size was inferred indirectly. For decades, Pluto existed in a liminal state, a planet in popular calendars and schoolbooks, an ambiguous object in scientific catalogs whose mass and composition were only weakly constrained. That ambiguity proved generative. It forced astronomers to invent and refine observational techniques suitable for the outskirts, improved spectroscopy to tease composition from nearly invisible light, stellar occultations to test for tenuous atmospheres, long baseline astrometry to pin down the orbit and infer mass. Those techniques slowly opened a window into what a world at the edge could be. Spectroscopic signatures, painstakingly collected with larger apertures and better detectors, revealed the presence of volatile ices on the surface. Methane was among the earliest molecules securely identified, its absorption bands appearing like fingerprints in the reflected light. Later, more sensitive instruments added carbon monoxide and hinted at the dominant role of molecular nitrogen. These detections were not dramatic, they were the work of accumulation, of photon after photon collected, modeled, and compared against laboratory spectra. The picture that emerged was a surface painted not in stone alone, but in a pale, shifting skin of volatile compounds, materials that, in the frigid conditions at the edge, are as mobile as water. The atmosphere of this remote body, when it was eventually probed, turned out to be as ephemeral and delicate as a glass bell. Stellar occultations proved decisive. When Pluto drifted across the face of a distant star, the star's light dimmed and refracted in a way that betrayed the presence of a gaseous envelope. Beginning in the latter half of the 20th century, such occultations showed that a tenuous atmosphere did exist, and pressure estimates emerged, surface pressures measured in microbars. To translate that into human terms, the air on Pluto is millions of times thinner than Earth's, a whisper in which molecules wander free over long distances before colliding. It is an atmosphere that is seasonal, that swells into being when the planet is nearer the sun and dwindles as it retreats into aphelion. Nitrogen. Those scientific revelations recast the 1930 discovery in a new light. What had seemed a mere notation on a planetary list became a case study in how the outskirts preserve and moderate physical processes. Pluto was no longer simply the ninth planet. It was a small world with a dynamic surface-atmosphere interplay, a body where volatiles move in a slow conveyor belt between frost and vapor, and where the thin sky could synthesize complex organics in hazes long before they settled as tarry residues on the ground. The discovery had thus set off a long sequence of investigation, stretching from the blink comparator's alternation to cameras and spectrometers more sophisticated than the founders could have imagined. The cultural reaction to the discovery and to the successive revelations was not merely a pedantic exercise in taxonomy. The initial enthusiasm about a ninth planet carried a mythic quality, a sense that the solar system had a clean, ordered tally and that humanity's understanding of its place could be neat and final. The slow, persistent work of characterizing Pluto insisted on an opposite virtue, recalibration. As measures refined, as the mass estimate was revised downward, as Pluto's role among a populous Kuiper belt became apparent, the narrative shifted. The story the object told moved from grandeur to subtlety, from a potential heavyweight at the boundary to an emissary of a crowded periphery. That shift produced emotional responses, nostalgia, even disappointment in some quarters. But it also produced a deeper, more honest curiosity. The decades that followed the discovery were an apprenticeship in remote sensing. Techniques were honed to read faint spectra and to time occultations with frenetic precision. New instruments captured haze layers and resolved surface features only when spacecraft made the journey decades later. Yet even before such close encounters, ground-based astronomy and space telescopes taught an important lesson that a small world at the edge can be rich in geological and chemical story. Mounting evidence pointed to seasonal volatility, to albedo contrasts that implied active transport of material, and to the possibility of internal differentiation in bodies that seemed, at first glance, too cold to rearrange themselves. This slow accumulation of knowledge also altered how the scientific community felt about the outer region's archival potential. The presence of volatile ices and a transient atmosphere suggested that surfaces on these bodies are not permanently fixed, they are rewritten in long cycles. At the same time, the coldness that characterizes the margins is also a preserver of molecules and structures that would alter or disappear closer to the sun. The discovery thus inaugurated a paradox. The very remoteness that makes observational science difficult also creates a conservatory of primordial chemistry. The outskirts preserve the past precisely because change proceeds at a glacial pace. Public imagination kept pace in its own way. The narrative of discovery. An observatory in a prairie night, a person at a blink comparator, the small moving dot revealed, became part of the cultural vocabulary. Children learned of 9 planets for generations. Calendars and textbooks absorbed that count and gave it weight. When scientific taxonomy later changed, when Pluto's status was reclassified as the understanding of the Kuiper belt matured, the emotional resonance of the initial discovery did not vanish. Instead, it became layered. The moment of 1930 remained a testament to human patience and to the peculiar romance of finding the distant by noticing slight motion against a static sky. There is a philosophical lineage in that romance. The act of detection at the edge is an expression of a certain epistemic humility. It acknowledges that the map is incomplete and that the periphery contains surprises not because they are dramatic, but because they are quiet and patient. To find a world like Pluto is to be confronted with the limits of immediate perception and to be compelled to extend methods of reading the faint into the realm of meaningful inference. The discovery thus stands as an emblem. The edge is not emptiness, it is a repository whose treasures require long attention. As instruments improved and as additional Neptunian bodies were catalogued, the meaning of the 1930 discovery grew more complex. Pluto was both individualized and situated. It retained its historical identity as the object first recognized beyond Neptune in the era of photographic plate surveys. Simultaneously, it became the first member of a much larger chorus of icy worlds whose collective properties taught more about the system's history than any single object could. The excitement that greeted the initial finding had broadened from the joy of adding another planet to the joy of discovering a new domain of inquiry. The later confirmation of atmospheric constituents, nitrogen as the principal gas, accompanied by methane and carbon monoxide, and the realization of surface pressures measured in microbars crystallized the scientific narrative. These are facts that link back to that first moving dot on a plate. The discovery was an entree, spectroscopy, and occultations were patient conversations that revealed the presence of a whisper of air and a skin of volatile ices. Together, these observations framed Pluto as a small, active world governed by climate cycles on timescales far longer than human seasons. In the end, the 1930 discovery is instructive for how human knowledge grows in the face of distance, incrementally, by instruments and techniques that extend the senses, emotionally, through a public narrative that invests meaning in new horizons, intellectually, by transforming a single data point into a gateway to a whole class of objects. Pluto's revelation was not a solitary triumph, but the opening of a long dialogue between observer and Edge 1 that would continue for decades, from photographic plates to flyby spacecraft, from naming ceremonies to spectral catalogs. The small moving light spotted on a blink comparator 50 years before the space age remains emblematic. It reminds observers that discovery is often the slow recognition of difference, that the margins of systems preserve histories because processes there are measured in epochs rather than hours, and that an idea of the edge, once tethered to a single object, can expand into a broader comprehension of how a system writes its own past into ice and orbit. The emotional and scientific excitement of the 1930 event may have been rooted in the hope of a new planet, but its lasting contribution was to point attention outward to the cold chemistry of nitrogen, methane, and carbon monoxide, to the fragile microbar atmospheres that breathe and collapse over centuries. What becomes unsettling to a mapmaker is not only when the edge retreats, but when the edge turns out to be populated. For decades, Pluto had been read as a solitary punctuation mark at the rim of the solar system, lonely, emblematic, and quietly didactic. Then, in the span of a few compressed years, that loneliness was contradicted by a cluster of discoveries, large, odd-shaped, and insistently alive in their implications. The margin ceased to be an exception and, almost overnight, announced itself as a crowded room. The consequence was not merely scientific, it was existential. The quiet boundary that once affirmed a simple narrative instead complicated every story that had relied upon that simplicity. The first of these late modern arrivals to seize public attention was an object that arrived with the force of a paradox. Observers discerned a small point of light so faint, so remote, that the immediate instinct was to treat it as a curiosity. But measurements kept accumulating. The object carried with it a satellite whose orbit could be traced. That orbit, in turn, allowed astronomers to calculate a mass greater than anyone had expected. The designation, Eris, an apt name given its capacity to stir contest and reflection, entered the catalog not merely as another member of the Kuiper family, but as a rival to the erstwhile ninth planet. For a moment, the arithmetic of the solar system seemed unsettled. Here was a body comparable in size, and perhaps heavier. The Eris's discovery did not happen as a dramatic image on a single night, but as a careful accumulation of photons, a patient choreography of sky surveys, follow-up observations, and the slow mathematical work of deducing mass from satellite motion. The instrument's ground-based telescopes, augmented by adaptive optics and space-borne infrared eyes, converse with each other, each offering a different register of truth. Thermal measurements suggested size and albedo. Reflectance spectra whispered of surface ices. The orbital dance of a small moon offered mass. The synthesis of these threads produced an unexpected result, a world at the outskirts that could no longer be dismissed as a mere bump on a list. It was almost contemporaneous with Eris were two other revelations that further complicated the periphery's census. One of them, Make, presented as a bright, methane-rich surface, a pale, reflective body whose spectral fingerprints showed methane ice in abundance, echoes of Pluto's chemistry, but not a mere copy. Its albedo painted it in a hierarchy register. Its composition suggested different thermal and collisional histories. The other, Haumea, was remarkable in form and story. Speeding through space with a rotation period measured in hours rather than days, Haumea was not spherical in any classical sense. Rapid spin elongated its shape into an ellipsoid and had, apparently, flung debris into space that later became a family of smaller bodies sharing rhythm. Each of these siblings carried a lesson. Their mere existence dissolved the comfortable, linear narrative that had turned Pluto into the sympathetic exile of schoolyard mnemonics. Instead, the edge revealed itself as a community with diversity. Some objects reflected sunlight with pearl-like brightness, others kept a darker, Tholen-stained visage. Some bore moons, evidence of collisions and captures, others exhibited shapes that testified to rapid spin or collisional stripping. Their orbits varied, some trapped in resonances with Neptune, others on scattered, eccentric paths that suggested dramatic encounters in the solar system's youth. Taken together, these discoveries painted the Kuiper Belt not as detritus, but as a dynamic. The emotional reaction within the scientific world was layered and revealing. There was exhilaration, of course, the raw delight that attends new data, new phenomena, new puzzles. There was also a quieter humility, a recognition that the taxonomies long taught in classrooms were provisional maps rather than immutable truths. And there was unease, not of the sort that dissolves inquiry, but of the sort that clarifies its stakes. If bodies comparable to Pluto existed in abundance, then the meaning of planet needed to be reconsidered. The debate that followed was technical, about dynamical dominance, hydrostatic equilibrium, and the physics of orbital clearing, but it was also cultural, because the word planet carries aesthetic and mnemonic weight. The result, formalized by a community attempting to reconcile method and meaning, that redefinition, while necessary, did not make the newly discovered bodies less wondrous. Each of the large Kuiper objects became a case study in how similar parental materials could yield divergent outcomes. Consider Eris. Its higher density compared to some peers suggested a greater fraction of rocky material, or a more compacted interior, perhaps the product of accretional circumstances different in subtle ways from those that built Pluto. Consider Haumea. Its elongated form and the presence of a collisional family signaled an ancient catastrophic event, an impact that redistributed angular momentum, scattered ejecta across similar orbits, and left the body shaped as much by violence as by time's slow hand. Consider Makemake, its spectrum's emphasis on methane and the apparent absence or thinness of a nitrogen-dominated atmosphere. The technical mechanisms that revealed these truths are a testimony to modern patience. Sky surveys, wide, repeated sweeps designed to capture moving points of light against the fixed stars, built the raw catalogs. Follow-up observations, sometimes executed across continents, pinned down orbits. Thermal infrared telescopes estimated sizes by measuring the faint glow of heat emitted at long wavelengths. Stellar occultations, moments when a distant star slips behind a trans-Neptunian object, offered precise constraints on size and atmosphere when timed and recorded carefully. Space telescopes and adaptive optics sharpened details that ground-based seeing could not. In the interplay of these methods, a more textured image of the distant population came into view. Beyond the morphological and compositional particulars, the existence of these siblings carried deeper implications for narratives of formation and migration. Planetary scientists had long understood that the early solar system was not a set of pristine, static orbits, but a theater of dynamical rearrangement. Giant planets migrated, resonances swept through populations of small bodies, and some objects were scattered outward into long, eccentric paths. The Pluto-nose bodies trapped in orbital commensurabilities with Neptune are fossil records of these migrations. Haumea's family reads like forensic evidence of a major collision, while the scattered disk's members bear the signature of close gravitational encounters. The new discovery, this layered archival quality revived and intensified a speculative dread that had been present in quieter forms since the first telescopic hints of the Kuiper Belt. If cold preserves, then multiple large cold bodies amount to multiple long-term repositories. Each sizable trans-Neptunian object is not only a geological and chemical experiment, it is also a potential conservatory of deep-time information. Differences in albedo, the presence or absence of volatile ices, and the depth of irradiation-driven organics imply varied capacities for preserving molecular signatures. Where nitrogen-rich ices lurk in protected basins, molecules may be sequestered and shielded from thermal cycling. Where impacts have churned the surface, older layers may have been exposed and overwritten, or That observation, in turn, shifted the contours of questions more speculative and profound. If one were searching for the solar system's earliest chemical recipes, patterns of isotopic ratios, concentrations of rare minerals, or preserved complex organics, the choice of where to look expands with every new large body discovered. Each object is a different kind of archive, offering different preservation regimes. Some are cold and calm, others bear the traces of cataclysm. The variety means that the outskirts are not a single kind of laboratory, but a distributed set of laboratories, each with its own way of locking memory into ice. The discovery sequence also reanimated hypotheses about unseen sculptors. The clustering of certain extreme orbits among distant trans-Neptunian objects sparked thought about the possibility of distant, massive perturbers, an idea that captured public imagination as the Planet 9 hypothesis. Whether or not such a distant planet exists, the very pattern of orbits, affected by resonances, scattering, and perhaps interlopers, points to a dynamical complexity richer than a static system of isolated bodies. The newly recognized siblings are thus not merely passive examples, they are active informants about the forces that have shaped orbital architecture across eons. Culturally, these discoveries forced a recalibration of narratives. The sentimental story that had attached to Pluto, its demotion, its anthropomorphic undertones, evolved into a broader, more generous realism. Pluto was no longer the pitied ninth, it became the first unearthed ambassador of a populous outer world. The public reaction contained surprise and, in some quarters, dismay at losing a simple mnemonic. Yet the deeper, quieter fascination that persisted was not with labels, but with process. The outskirts revealed themselves to be laboratories of slow change and long memory, and the existence of multiple large bodies invited a change in perspective, from an emphasis on endpoints to an interest in systems. For those who study preservation across vast durations, the consequences were concrete. Multiple large bodies imply multiple repositories of primordial materials. The cold of the Kuiper Belt is not merely an absence of warmth, it is a method of conservation. The chemistry of organics, the isotopic fingerprints of volatiles, and the structural legacies of collisions can all be held in forms that resist the erasures common to inner worlds. If, in speculative thought, one considers the possibility of traces, natural or otherwise, from deep and distant epochs, the proliferation of sizable, cold objects increases the search space where such traces might survive. What remains striking is the human lesson embedded in the scientific finding. The edge was never meant to be a single dot on a chart. It has its own crowded topography of mass, orbit, and history. The discovery of Eris, Haumea, Makemake, and their kin replaced a narrative of solitude with a narrative of plurality. That shift broadened the kinds of questions that could be asked, not only, what is this one world, but what does a population of such worlds tell us about origins, preservation, and the dynamics that rearrange solar systems? The quiet drama of distant bodies spun out across centuries and eons became a chorus. Each new member of that chorus changes the music, the timbre of chemistry, the rhythm of orbital. What does a word do when it is asked to hold an entire worldview? The question feels small until it is pressed up against the cold grid of the outer solar system. In 2006, a single decision about a single word planet forced a reckoning not only with classification, but with how humanity rearranges mental maps in the face of abundance. The choice was technical on its face. 3 criteria, written as a compact test. But the decision unfolded like a social seismograph, registering professional insistence, pedagogical habit, and cultural attachment in one collective tremor. Pluto, whose existence had long occupied a sentimental fulcrum between telescopes and schoolchildren, found itself at the center of that tremor. In the end, the body's failure to satisfy the third criterion, clearance, the International Astronomical Union's 2006 definition, was meant as a practical tool. It proposed 3 requirements for any body to wear the label planet. The first was straightforward, it must orbit the Sun. The second was a structural condition, hydrostatic equilibrium, the idea that the object must be massive enough that its self-gravity pulls it into a nearly round shape. The third requirement moved decisively into dynamics. A planet must have cleared its neighborhood. That phrase, deceptively plain, encodes a specific physical claim. It means that over the history of the system, a planet must have become gravitationally dominant in its orbit, removing or assimilating most other bodies of comparable size near its path, such that its gravitational center. On paper, the rule reads as tidy logic. In practice, it is an operational judgment about history and influence. Clearing the neighborhood is not a measure of absolute emptiness. It is a relative statement about dominance. Jupiter, for instance, is so massive that its gravitational influence has shaped the small body populations across vast swaths of the solar system. It shepherds asteroids, scatters comets, and imposes resonant structures. Pluto, by contrast, shares its orbital region with many Kuiper Belt objects. It participates in a crowded outskirts, not as a solitary sovereign, but as a member of an ensemble. The Kuiper Belt is a populous periphery, an extended archive of icy bodies formed in the outer reaches of the primordial disk, and Pluto. That dynamical framing was not invented to be cruel to sentiment. Rather, it was a response to new data. Beginning in the late 20th century and accelerating with improved telescopes and survey programs, astronomers began to catalog many substantial objects in the trans-Neptunian region. Eris emerged as a paradigmatic disruptor, a body whose size and mass rivaled Pluto's, whose discovery implied that any simple list of planets anchored at 9 would be inadequate. If Pluto were to remain a planet on grounds of size alone, then parity suggested that many other similar bodies might demand the same status. Scientific method prefers definitions that scale, rules that can be applied consistently once new members are found. The core of the controversy returned repeatedly to the third criterion. What does it mean, practically, to have cleared an orbit? The phrase compresses a long arithmetic of time, mass, and dynamical interaction. A massive planet clears its neighborhood by accreting, ejecting, or otherwise dominating the smaller objects that share its orbital zone. Over billions of years, those interactions concentrate mass and reduce the number of sizable neighbors. An object that shares its path with many co-orbital companions, objects of similar dynamical standing, has not done that work of dominance. Pluto, lodged in a 32 resonance with Neptune and accompanied by a populous belt of Plutinos and classical Kuiper objects, fits the latter description. But scientific statements, even when expressed in technical terms, are always interpreted through human frameworks. For the public, schoolchildren, and many educators, the image of the solar system had become structured by mnemonic comfort: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. 9 felt tidy, 9 felt complete. When the decision was announced, Pluto reclassified as a dwarf planet, one among several round bodies that did not dominate their orbits. The emotional reaction was immediate. The response was not a uniform outcry in the laboratories alone. It spilled into newspapers, into classrooms, into the quiet interior of people's imaginations. The reclassification felt, to many, like a small erasure, an endpoint removed. Scientists, for their part, showed a complex mix of practical acceptance and philosophical discomfort. The pragmatic view emphasized clarity. A definition that scales with growing discovery is useful. It prevents the mental contortion of calling dozens or hundreds of comparable objects by the same title simply because a preferred number feels neat. But others argued that the IAU's choice privileged dynamical history over intrinsic characteristics. They pointed out that the criterion, clearing the neighborhood, is inherently time-dependent and contextual. Whether a body clears its orbital zone is sensitive to the system's particular architecture and to the timescale considered. In another star system, or under different migratory histories, the same action could play out. That tension is not merely academic. It addresses how humans think about belonging in layered systems. Pluto's demotion was a decision rooted in orbital sociology, how bodies interact and compete under gravity, rather than a judgment about geological vitality. Indeed, the discovery of active geology on Pluto in 2015 would add an ironic subtext to the 2006 decision, a small world of complex, surprising activity rendered lonely by a lexical reclassification. The planetary label, as used historically, blended several senses: physical mass, roundedness, dynamical dominance, cultural familiarity. The IAU's effort to disentangle those senses into a crisp operational definition exposed. Beyond the institutional moment, the debate provoked reflection on meanings of scale and sufficiency. The Kuiper Belt's discovery of many comparable objects forced a reorientation from an old model of isolated realms to a model of richly populated peripheries. Pluto ceased to be an exceptional endpoint and became an index of a larger population. That reframing expanded curiosity. The reclassification, though emotionally painful for some, was scientifically clarifying. It focused attention onto the outer system's diversity, encouraging a morphology of inquiry that treated dwarf planets not as second-rate planets, but as an essential class with specific kinds of information to offer. Pluto's roundness remained noteworthy. Its capacity to hold an atmosphere, to display active geology, to register seasonal. The wider debate also illuminated how definitions in science have consequences that reach into pedagogy and culture. Textbooks had to be rewritten, classroom routines had to adapt. The simple mnemonic that organized many people's childhood cosmologies had to yield to a more nuanced reality. That transition was not merely administrative. It was also ethical in a small way. It reminded educators and communicators that the lines drawn on maps are provisional, subject to revision as instruments sharpen and as discursive needs change. The public conversation about Pluto's status therefore became a case study in scientific literacy, how communities absorb corrections, how cultural attachments shift. But the argument did not finish with a single vote. The redefinition provoked new proposals and continued discussion. Suggestions surfaced for alternative taxonomies that emphasized geophysical qualities rather than dynamical dominance, proposals to create a richer taxonomy of planetary bodies across contexts, and debates about how to handle exoplanets and free-floating planetary mass objects. Some practitioners argued that the IAU's definition was too solar system-centric in its explicit reference to orbiting the Sun. Others proposed terms that would be more universally applicable in an era of exoplanet discovery. The intellectual ferment that followed was healthy. Language needed to be robust enough to accommodate discoveries that did not fit neat history. Through all of this, an important conceptual lesson emerged. Labels do not reduce phenomena, they focus attention. Reclassifying Pluto did not make its frozen plains less real, nor did it diminish the repository of information it held about planetary formation. If anything, the debate deepened the sense that the Kuiper Belt is the place to read the system's early script. The redefinition compelled a move away from a narrative centered on a handful of planets to a narrative that treated the outskirts as a crowded, consequential archive. In that sense, Pluto's demotion served as a conceptual pivot. The erstwhile ninth planet became a flagship example of a new category, a prototype that increased interest in trans-Neptunian populations rather than dampening its frode. Emotionally, the story left traces. For some, the reclassification felt like the loss of a friend from a household roster. For others, it represented a maturing of scientific practice, the willingness to revise cherished categories when evidence demanded it. The public ritual that followed, ranging from internet memes to earnest opinion pieces, revealed a cultural economy of meaning, making unrelated to mass and orbit. People projected identity onto celestial bodies because humans long for comprehensible archetypes to hang on to when thinking about otherwise dispassionate mechanics. Labels like planet function as mnemonic anchors. When anchor points change, memory adapts unevenly. There is also a philosophical echo in the outcome. Belonging is not merely a property of an object, but a relation it bears to its environment. To call Pluto a planet by the IAU's definition would have been to flatten that relational quality into a static predicate. The redefinition, instead, foregrounded relationality, how mass, motion, and historical interactions co-constitute status. The outer solar system's crowdedness meant that the language of solitary dominion no longer fit reality. A new grammar was required, one attentive to ensembles and to the varied roles that bodies can play in a system's long temporal dance. In practical terms, the decision's long-term consequence resembled a redirect rather than a dismissal. Pluto's scientific profile flourished. The questions it posed: how do volatiles migrate in weak sunlight? Can small worlds sustain internal warmth? What does long-term preservation in ice look like? Became central to planetary science. The dwarf planet category made room for intentional study of bodies that share orbital companionship. That has epistemic value. It emphasizes comparative study across a range of sizes and dynamical contexts, enriching theories of accretion, migration, and preservation. The demotion was not a removal from inquiry, it was a reclassification that reframed inquiry's targets. Finally, the episode invites a cautionary, reflective posture toward the work of naming. When humans create categories, they are not merely labeling the world, they are making instruments for thought. The IAU's 2006 decision exemplified the tensions inherent in that work: the desire for operational clarity, the need for definitions that scale, and the recognition that cultural attachments complicate purely technical decisions. The case of Pluto is less a parable about losing a planet than a story about how a community of knowledge chooses to order experience in the face of new evidence. It is evidence, too, of the outskirts' capacity to surprise. The Kuiper Belt has many voices, and the emergence of those voices Pluto's status shifted because it was not alone, and because size alone was not sufficient to secure a place on a list designed to reflect dynamical history and dominance. Yet the body's geological vigor, its seasonal atmosphere, its role as an archive of primordial chemistry, all of those remain unaltered by human decree. The wider moral is that scientific classification is a conversation among facts, models, and human meanings. Labels can be useful waypoints, but they are provisional. The outskirts of the solar system insist that as knowledge deepens, language must stretch. The 2006 verdict was one such stretch, a rephrasing that recognized an abundance where once there had seemed to be a solitary endpoint. It did not make Pluto. What does it do to a culture when a speck of light on a century-old photographic plate is finally resolved into a landscape? That question is both practical and existential. A pixel becomes a place, and with the translation comes a cascade of surprises, reconfigurations of expectation, and a renewed ability to listen to deep time. The New Horizons encounter in 2015 turned that philosophical moment into a concrete event. After decades of patient observation, banked trajectories, and engineering that trusted precision over drama, humanity received the first close-up portraits of Pluto. What arrived in the data stream was not the flat, inert ball of ice some had imagined. It was a world with texture, motion, and an austere sort of liveliness. The approach itself was an exercise in telescoped patience. New Horizons was an ambassador built of fuel budgets, antenna patterns, and spectrometers, an instrument harmonized to travel for years, then to turn with disciplined choreography to collect what photons it could in the thin light of the outer system. As the probe closed, its cameras and sensors were trained like a succession of listening devices, long-range imagers building orientation maps, spectrometers reading the subtle fingerprints of surface composition, radio experiments tracking mass distributions, and particle detectors sampling the subtle interaction between a fragile atmosphere and the solar wind. Every instrument performed a kind of reading. Together they composed a grammar for a world that had, for most of the first close images, produced a collective recalibration. Smooth expanses came into focus beside jagged relief, pattern and irregularity alternated like handwriting. The famous heart of Pluto's Sputnik Planitia dominated many frames, an immense pale basin filled with volatile ices whose cellular texture resolved into large polygonal cells. Those polygons were not mere aesthetic accidents, they were signatures of convective overturn, where solid nitrogen behaves like a viscous medium under the influence of slight thermal gradients. The idea of convection here felt almost scandalous, a small, frigid world engaging in a process usually associated with hot planetary interiors. The presence of such motion elevated the mountains rose with abruptness against low plains, steep, jagged blocks of water ice that, at Pluto's temperatures, are as strong and as mountain-forming as basalt would be on Earth. Their faces were scarred, terraced, and in places freshly exposed, as if the planet had revealed a palimpsest of episodes within its crust. Sight of these ranges contradicted the expectation that small bodies could not support significant relief. The mechanical properties of frozen water at tens of kelvins permit the formation and preservation of relief, and New Horizons images made that physical truth visually undeniable. Between these peaks lay landscapes of blade-like ridges, long, sharp methane ice features that rose in serrated fields. These bladed terrains suggested a process of deposition and sublimation operating with geological slowness. Methane ice, deposited over epochs and then sculpted by sublimation into long vertical forms, gave the ground a texture both alien and unambiguously geological, a morphology formed not by flowing water but by the patient interaction of phase changes in cryoclimates. Elsewhere, dark, rust-colored regions, coated with tholins formed by slow irradiation chemistry, stretched across basins, testifying to chemical transformations that take place under a weak sunlight and a steady drizzle of cosmic. Perhaps the most arresting discovery was the sense of youth in many terrains, where expectation predicted a pockmarked, heavily cratered face. The record of billions of years of impacts, the surfaces in many areas appeared comparatively fresh. Crater counts in Sputnik Planitia, for instance, were unexpectedly low. Such relative lack of bombardment implies resurfacing, processes that erase impact scars and renew the visible skin. The mechanism at work here is not volcanism in the temperate sense, but the interplay of volatile mobility and cryogeological dynamics. Nitrogen, the most volatile of Pluto's major surface constituents, sublimates and recondenses seasonally. It flows slowly as glaciers, and within large basins, convective processes. The atmosphere, though tenuous, emerged as another unexpected actor. New Horizons observed layered hazes reaching tens to hundreds of kilometers above the surface, scattering sunlight into twilight blues and painting the limb with delicate stratification. These particles are not inert, they are part of chemistry that lifts simple molecules into a diffuse reaction chamber. UV photons and energetic particles break methane and nitrogen into reactive fragments that can recombine into complex organics. The tholins that coat darker terrains when they settle. The planet's thin breath, a seasonal exhalation of nitrogen and methane when perihelion warms the face enough, is part of a cycle that moves mass between solid and gas. A theme threaded through these revelations. Mobility and dryness existed together. The dryness here meant the apparent absence of standing liquid water at the surface. No oceans, no rivers, yet mobility was abundant in other registers. Ices flowed, sublimated, and convected, gases rose and fell, particulate hazes fell like a slow snow. The word dry therefore required nuance, dry in the hydrological sense that defines habitability on Earth, but transactional in terms of volatile migration. There were no liquid seas, yet Pluto's skin was not inert. It was interacting with its thin atmosphere, rearranging mass and albedo patterns on timescales that outlasted human attention spans but were active in geological terms. There were also hints, not confirmations of processes that reached below the frozen crust. Some morphological cues suggested that internal heat, perhaps from long-lived radioactive decay or residual energy from ancient accretion and collisions, might have been sufficient to permit localized slurries or even subsurface reservoirs in the past. The idea of a subsurface ocean, while speculative, gained empirical plausibility from the planet's reoriented mass distribution, the presence of tectonic fractures, and the patterns of uplift and collapse around basins. If liquid pockets existed beneath the ice, they would be briny, ammonia-rich slurries whose phase behavior at low temperatures allows liquid to persist in spite of the chill. New Horizons could not directly probe such depths, but Beyond the physical surprises, the mission reframed human relationships to the edge. The images, mosaics stitched from tens of thousands of photons collected across hours and then transmitted across nearly 5 hours of one-way light time, arrived like dispatches from a very different register of time. Each transfer was a reminder of scale, the probe's radial packets, the relay of data, the patient reassembly of high-resolution mosaics back on Earth. There was a ritual to the reception, one enacted by institutions, observatories, and publics that had watched for decades. The reaction was as much about humility as it was about triumph. The data was a corrective to assumption. Remote points on a plate are places with histories, and places keep secrets. The science that followed the image release did what science always does. It took an aesthetic surprise and translated it into quantifiable models. Measurements of topography suggested mountain heights of kilometers, spectral analyses defined the proportion of nitrogen, methane, and carbon monoxide across regions, thermal models reproduced convective motion in volatile-rich basins when certain thickness and viscosity thresholds were met. These models created a coherent narrative that reconciled the visual evidence with physics, a basin deep enough to collect a thick volatile layer, insulation and slight internal warmth to drive convection within that layer, and topography strong enough to preserve relief. The interplay of these elements produced the observed landscapes. New Horizons also refined the sense of diversity in the outer system. Pluto's geology, while surprising, was not generic in the Kuiper Belt. Different trans-Neptunian objects showed different proportions of volatiles and irradiation products. Some, like Eris, appear brighter and more reflective, perhaps coated by cleaner ices, while others wear darker veneers of complex organics. The variety exposed by New Horizons argued for cautious extrapolation. The outer system contained a gallery of outcomes rather than a single archetype. Pluto is a particularly complex one, perhaps because of its size, binary relationship with Charon, and particular collisional past. Whatever was true for Pluto need not be true for all Kuiper denizens. The mission taught the virtue of speculation expanded in the wake of the flyby, but remained bounded by physics. If the outskirts are preservers, cold, conservative, slow-then territories on these bodies that sequester volatiles or isolate strata could be exceptional repositories of ancient chemistry. Sputnik Planitia, for instance, functions as a cold trap, an accumulation zone where nitrogen concentrates. Such basins could harbor strata that, if sampled, would present a layered record of atmospheric and climatic variation across many orbits, an archive written in frost. The idea pressed the imagination. Where inner planets have erased early records through tectonics and life, the outer system preserves. A cold planet is a slow librarian. The mission turned such metaphors into actionable hypotheses, target cold traps. There was also a pedagogical effect. Textbook stories that anchored the planetary lineup in 9 neat entries were rendered historically complicated by these intimate images. The argument about labels, what counts as a planet, remained relevant, but now seemed less consequential in the face of the richer question, what do these bodies preserve? The New Horizons images shifted attention from nomenclature to mechanism. Pluto's scientific value was not diminished by taxonomy, it was amplified by the ability to read its surfaces and to compare them with the spectra of other distant objects. The mission's legacy contains a humility that is almost ethical. The resolution of a world into terrain and texture is an act of translation. The faintest photons are given civic voice. Those voices told of convective basins, of glacial flows of nitrogen, of mountains composed of rigid water ice, of chemical veneers formed by patient irradiation. They also told a quieter story about care and patience in observation. New Horizons demonstrated that when the instruments are designed to trust long timescales, years of cruise, hours of data transmission, the cosmos can reveal details that upend tidy narratives. Finally, the flyby served as a reminder of limits. No single probe can answer all questions. New Horizons left as it arrived, fast, ephemeral in its proximity, but rich in the legacy of data. Its images invited follow-up orbital missions that could map temporal variability across seasons, landers that could sample strata, suborbital penetrators that could test the structures beneath. The discoveries demanded continued curiosity, and they argued for a long view of exploration, one oriented to decades, not headlines. As a document of possibility, the New Horizons encounter reframed what it means to know a distant place. A pixel became a place, the place proved unexpectedly active, and the lessons accumulated into a larger philosophical posture. The margins hold stories written in slow inks. Pluto was dry in the sense that it lacked liquid water on its surface, but it was animated by other forms of mobility, volatile convection, haze-driven chemistry, and the persistent work of irradiation. It was not a quiet tomb, but a conservative archivist, one that preserved early solar materials while still playing a subtle, ongoing geological role. In the atlas of the solar system, New Horizons had turned a punctuation mark into a landscape, and in doing so, it expanded the repertoire of how a civilization reads its margins. What does it mean for a single small world at the margin to become an interpretive key for an entire region of space? That question sits at the heart of Pluto's expanded significance. Once relegated to the end of a nursery rhyme about the solar system, Pluto has been recast by observation and imagination into something much more consequential: an emissary, a readable sample, from the Kuiper Belt, and therefore a lens through which the origin, dynamics, and preservation of the outer solar system are understood. Pluto's value is not symbolic alone, it is methodological. Because it is both large enough to retain a differentiated interior and volatile envelope in places, and small enough to remain strongly influenced by its collisional and dynamical environment, it occupies an intermediary regime where many processes can be observed in chiaroscuro. In that in-betweenness lies a comparative advantage. When New Horizons revealed plains that convect, mountains of water ice, and a seasonally collapsing atmosphere, the discovery was not an isolated revelation, but the opening of a comparative laboratory: what happens elsewhere in the belt when sunlight thins and time expands. Comparative planetology is not an academic luxury here. It is the only reliable way to separate local contingency from systemic law. Pluto's geology: the flowing nitrogen plains of Sputnik Planitia, the mountainous water ice ranges, the bladed methane ridges, must be read against other dwarf planets and trans-Neptunian members. Differences in surface color, volatile inventory, degree of resurfacing, and presence or absence of atmospheres trace a matrix of formative conditions and evolutionary paths. Each body becomes a controlled variable in an experiment with the primordial disk as the unknowable control. Eris forces the first comparison. Larger or as large as Pluto in some measurements and brighter in reflected light, Eris posed the conceptual challenge that changed everything. If there are many large icy bodies beyond Neptune, the simple list of planets becomes arbitrary. But the contrast between Eris and Pluto also reveals process. Eris's high albedo suggests either a cleaner, younger veneer of volatile ice or an efficient resurfacing process that keeps irradiation products from darkening its face. This points to differences in collisional history or thermal state. If Eris retained or recently accreted a more pristine layer of nitrogen or methane, why did Pluto develop complex tholins and varied landscapes? Is it a question of initial Haumea illustrates the power of collision as an archetypal sculptor in the Kuiper Belt. Its rapid rotation, elongated shape, the family of fragments and related orbits, and its ring point to a violent history, an impact that stripped outer layers, redistributed angular momentum, and produced daughter fragments. In contrast to Pluto's comparatively intact structure and large satellite, Charon N, itself a probable collisional product, Haumea's morphology shows the range of outcomes collisions can produce. Where Pluto's binary dance with Charon hints at a giant impact that left two bodies bound to each other in a permanent duet, Haumea's broken symmetry shows how similar, energetic events can lead to fragmentation and spin-up rather than quiet pairing. The study of both bodies therefore supplies a statistical basis for assessment. Make and its quieter, methane-rich visage add a further dimension. Its spectrum emphasizes methane and less evident nitrogen, a signature that raises questions about volatile inventories and thermal histories. Does Make preserve a different volatile budget because its accretion zone was richer in methane, or because subsequent thermal events removed nitrogen selectively? Such distinctions matter because they map onto broader hypotheses about the protoplanetary disk's radial chemistry. If gradients in temperature and composition produce local biases in the ice mix, then the present-day diversity among dwarf planets is a fossilized record of that chemical geography. Sedna and the distant detached objects extend the inquiry into dynamics. Their extreme orbits, so far removed from Neptune's immediate influence, suggest perturbations, either from passing stars during the Sun's early cluster phase or from hitherto unseen massive bodies in the distant solar halo. If Sedna-like orbits were sculpted by stellar encounters, then the outskirts preserve a chronicle of the Sun's birth environment. If they required a distant planetary mass perturber, then the outer system is telling a secret about massive architectures that lie beyond current detection. Either way, the presence of such detached bodies multiplies the interpretive possibilities for Pluto. Is Pluto representative of a local Kuiper population, or is it one part of a gradient that extends into the solar hinterland? Charon, Pluto's large companion, clarifies another axis of interpretation: binary evolution. Pluto and common barycenter, their mutual interaction yields a dynamical laboratory for studying tidal evolution, angular momentum transfer, and surface exchange. The system's shared geology, evidence of resurfacing on both bodies, hints of tectonic fracturing, and asymmetries in coloration, suggests material exchange and interlocking thermal histories. This binary partnership gives insight into satellite formation mechanisms across the belt. A body's companion is not merely a satellite, it is a partner that can keep internal heat alive a little longer through tidal interactions, alter the distribution of the Kuiper belt itself emerges as the macro context for these comparisons. Pluto's orbit and physical state helped confirm that the outer system is not a sparse halo, but a dense, stratified population with resonant structure, scattered components, and dynamically stable classical belts. Pluto's 3-2 resonance with Neptune, shared by the Plutinos, is a fossilized trace of planetary migration. The Nice model and its descendants suggest that giant planets wandered, swept small bodies into resonances, and scattered others outward. Pluto's existence in resonance, its eccentricity and inclination, and a distribution of other resonant objects give empirical constraints on the timing and amplitude of planetary migration. In short, Pluto's dynamical parameters are that reordering matters for preservation. The Kuiper Belt is at once a sculpted and a conservative archive. Gravitational perturbations overwrite orbital memory, but the chemical and isotopic signatures locked into ices are remarkably stable in the cold. Pluto teaches that preservation is selective, mechanical rearrangements can redistribute bodies and create collisional families, while low temperatures lock molecular structures into long-lived states. By comparing isotopic ratios of nitrogen, carbon, deuterium content in water across multiple dwarf planets and comets that sample the belt, researchers can reconstruct radial mixing processes in the disk and the provenance of volatiles delivered to the inner planets. Pluto's atmospheric dynamics add a further comparative lever. Its tenuous nitrogen-methane envelope, seasonal and intermittent, demonstrated that even small, cold worlds can sustain active volatile cycles. When contrasted with Makemake, which appears to lack a comparable atmosphere, or Eris, whose bright surface suggests different resurfacing or atmospheric histories, Pluto reveals how delicate balances of gravity, volatile inventory, and orbital distance can produce or preclude atmospheres. The presence or absence of atmospheres shapes surface chemistry by enabling photochemical haze formation aloft and subsequent deposition as tholins. Comparing haze production rates and surface coatings across objects thus illuminates chemical pathways and exposure ages. Beyond the immediate physical sciences lies a speculative but disciplined domain, deep-time preservation of complex molecules and, hypothetically, human-made artifacts. The physics is simple, low temperature slows chemical kinetics, and a dearth of aqueous alteration reduces degradation pathways. If complex organic macromolecules were synthesized in the early disk or delivered from interstellar grains, their alteration on the Kuiper Belt surfaces would be slow. Comparing spectral signatures of organic residues across multiple objects helps quantify irradiation processing and the thickness of protective coverings. If some bodies preserve cleaner volatile veneers that periodically reseal ancient layers, they become the most promising targets to read primordial chemistry intact. Instrumental method follows theory. The role of telescopes, occultation campaigns, infrared surveys, and targeted flybys becomes apparent in this comparative enterprise. Pluto began as a moving dot on glass plates. It matured through spectroscopy, occultation-derived pressure profiles, and, finally, a close flyby that delivered high-resolution imaging and in-situ particle data. Each observational modality brings its own bias and strength. Thermal infrared constrains size and albedo. Spectral reflectance attributes surface composition. Occultations reveal atmospheric structure. Flybys resolve morphology and map microtopography. A systematic program that applies these tools across the Kuiper cohort. A comparative planion of dwarf planets, Plutinos, scattered disk. The narrative urgency is not academic. Understanding the Kuiper Belt bears on broader planetary science, how volatiles were distributed in the early solar system, how water and organics could have been delivered to the inner planets, and how planetary systems rearranged themselves over time. In exoplanetary terms, the Kuiper Belt is an accessible analog for outer debris disks seen around other stars. If the structure of our belt, resonant trapping, scattered populations, detached long-period members, is legible through Pluto and its peers, then distant debris disks can be interpreted with better fidelity. Pluto thus becomes a Rosetta Stone not only for the solar system's history, but for comparative planetary archaeology across the galaxy. There is, finally, a philosophical dimension to Pluto's role. Its demotion from schoolroom planet to a dwarf planet within a populated belt was less a loss than a reorientation, from a telescopic endpoint to an archival node. Its surfaces, atmospheres, and binary dance with Charon reframed questions about belonging, dominance, and memory. Where once a single label sufficed to tell a tidy story, now a pluralistic conversation emerges. Each dwarf is a distinct volume in a library, and their differences are the footnotes that allow the reader to reconstruct the larger manuscript. This reframing creates demands for the future. The next phases of exploration will not be solitary flybys alone, but comparative missions, orbiters that monitor seasonal cycles, landers that sample strata in cold traps, spectral campaigns that compare isotopic signatures across many objects, and coordinated surveys that map dynamical families and collisional lineages. These are not fanciful additions. They are necessary to move from anecdote to theory. The Kuiper Belt is a crowded archive, and only a distributed program of observation can read it coherently. Pluto's lesson is both practical and existential. Practically, it demonstrates that a marginal world can be intensely informative. Its geology, atmosphere, and binary dynamics constrain models of planetary migration, volatile transport, and collisional evolution. Comparatively, its differences with Eris, Haumea, Makemake, Sedna, and others create a mosaic from which general principles can be inferred. Existentially, Pluto offers a teaching in patience that time in the outer solar system is different, that processes stretch and slump in ways that human attention must accommodate, and that preservation in the cold permits a fidelity of memory otherwise lost closer to the star. Viewed from this perspective, Pluto stops being a single lonely point and becomes a node in a conversation, a voice through which the Kuiper Belt speaks. That voice insists on a different cadence of inquiry. It asks listeners to accept season scales that exceed lifetimes, to read tholins as a slow chemistry, to interpret resonances as fossilized planetary migrations, and to treat cold not as sterile absence but as a conservator's hand. In the comparative theater of dwarf planets, Pluto's role is clear. It is a translator between the visible present and the frozen past, a specimen that helps decode the Kuiper Belt's language. To listen, patiently and with instruments attuned to slow processes, is to hear the solar system tell its oldest stories in the long 11. Hypotheses about Pluto's future. What does a long, lonely orbit do when it is nudged? That small question, about the effect of a gentle shove on a patient path, frames the future of Pluto. It is tempting to imagine the dwarf planet as fixed, a bead threaded on a celestial wire whose pattern will not change. But orbits are histories writ in motion. They are conversations between masses that continue long after any single actor has been named. Pluto's present choreography is stable in a practical sense, yet that stability is a kind of conditional peace, dependent on balances that can be altered by agents large and small, near and far. To think about Pluto's future is to think about what can disturb balance at the margins. On human timescales, the answer feels simple. Pluto's 32 resonance with Neptune protects it. For every 2 circuits Pluto makes, Neptune makes 3. Their orbital rhythms avoid close approaches and establish a dynamical etiquette that has held for billions of years. That resonance is not a whimsical constraint, but a robust, dynamical lock, a mechanism that confines chaos and shepherds trajectories. In the language of celestial mechanics, it is a stabilizing resonance. In the language of metaphor, it is a rehearsal of trust between worlds. Because of this resonance, drastic near-term changes to Pluto's orbit are unlikely. Its present path will persist long enough for numerous human generations to look up and repeat what the last. Yet stability here is probabilistic, not absolute. Kuiper Belt is not an empty plane, it is a crowded field of neighbors, objects that wander in a three-dimensional disk, some small and inert, some large enough to exert non-negligible gravitational influence. Close encounters with sufficiently massive Kuiper Belt objects, COBAOs, could, in aggregate or in a single event, nudge Pluto's eccentricity or inclination. Collisions, though infrequent compared to the inner system, remain possible. The belt's population is small compared with the early planetesimal swarm that once stamped the young solar system, but even rare collisions carry memorable consequences when they happen in a low-energy, cold environment. An impactor the size of many kilometers striking Pluto could excavate, deposit fresh material, modify. There is a gentle spectrum of futures to consider, each governed by probabilities that shift with timescale. Over tens to hundreds of millions of years, slow, chaotic diffusion, the gradual change of orbital elements due to the small cumulative tugs of many bodies and the subtle nonlinearities of resonant overlaps, can alter Pluto's orbit modestly. Such changes would modulate insolation cycles, perhaps amplifying or damping seasonal volatility. Increased eccentricity would bring the dwarf planet closer at perihelion and farther at aphelion on some cycles, altering the degree of atmospheric collapse and the timing of frost migrations. In turn, climate shifts on scales of many Plutonian seasons would rearrange surface textures. Cold traps might migrate. More dramatic possibilities, rarer but not impossible over giga-year spans, involve violent encounters. A sufficiently close gravitational interaction with a large Kuiper object could scatter Pluto onto a markedly different orbit, one that places it outside the protective resonance. In extreme cases, scattering can transfer enough energy to eject a body from the solar system entirely, flinging it into interstellar space to become an ice-mantled wanderer around the galaxy. That outcome, while unlikely on shorter timescales, is not forbidden by mechanics. Historical precedent in simulations of planetary system evolution shows that small bodies can migrate inward or be hurled outward when resonances shift or when massive perturbers rearrange population architecture. In Pluto's future, such a fate would be contingent on it. The notion of ejection is kinematically simple and emotionally strange. To be cast out of one's natal system is to become, in a literal sense, an exile. Yet the physics of such exile creates a counterintuitive conservation. The very cold that made Pluto an archival conservator would then make it an interstellar courier. Absent the intense heating and chemical turnover of the inner system, organics and isotopic records could remain frozen and legible for unimaginably long durations in the deep chill of interstellar space. A body flung from the solar system becomes, paradoxically, an artifact of preservation, carrying the system's early recipes across parsecs. Different still are perturbations wrought by forces not resident within the Kuiper Belt, passing stars close enough to perturb the outer reaches, and the gentle but persistent tug of the galaxy's tidal field both alter distant orbits on giga-year timescales. Pluto, sitting between the relatively snug orbits of the giant planets and the far, loose sheath of Oort cloud comets, is somewhat sheltered compared to those far-flung bodies, but it is not completely immune. A close stellar passage in the Sun's future could seed resonant chaos or shift collective momentum. The long-term architecture of the solar frontier thus remains vulnerable to external tides, however subtly. The possibility of an as-yet undetected distant planet, the speculative Planet 9, if real, would further complicate the future. A distant, massive perturber could sculpt eccentricity. Collision scenarios demand special attention because they are the most immediately transformative. The energy of an impact depends not just on the size of the projectile but on relative velocity and angle. In the cold outskirts, relative velocities can be lower than in the inner system, but if a high-speed collision were to occur, the consequences range from local excavation to wholesale fragmentation. Fragmentation can seed rings and satellites. It can also disperse a cloud of debris that, given time, might reaccrete into smaller bodies and generate a collisional family, an extended testimony in orbit about the event. Even subcatastrophic impacts can be geologically meaningful. The exposure of subsurface brines or antifreeze-rich slurries could allow short-lived cryovolcanic activity, elevating local temperatures and creating chemical microearthquakes. The presence of Charon complicates and cushions these scenarios. Pluto and Charon, locked in a mutual dance about a shared barycenter, present a system with internal checks. Tidal interactions between them have long since damped into synchronous rotation. Charon's presence stabilizes certain aspects of Pluto's spin and modulates potential reorientations. At the same time, Charon is a participant in collisional history. The leading hypothesis for its origin is a giant impact that left the pair bound and endowed both bodies with shared scars. Any future major collisional event affecting Pluto would likewise affect Charon, possibly altering mutual orbits or creating tertiary debris systems. The binary system's inertia is what lends emotional texture to these cold calculations is the implication for preservation and for narrative. Pluto's present identity as an archivist, a conservator of early volatiles and irradiation chemistry, is resilient in some disruptions and vulnerable in others. Ejection into interstellar space preserves material but removes the body from the solar system's contextual archive. It would carry the system's story outward, but it would make the story harder for the Sun's remaining ensemble to read. A destructive collision risks scrambling local stratigraphy, yet it can create secondary archives, fragments whose surfaces, repeatedly exposed, might lock in radiation products and layered deposits differently than a single intact shell would. In either case, the underlying physics stubbornly insists that memory is redistributed. From a human vantage, these futures exert two contradictory impulses. One is an urgency to observe and sample while the present configuration holds, to send orbiters, landers, cryobots, and sample return missions that would secure physical testimony before chance alters the ledger. The other is a patient recognition that deep time is patient as well, even if dramatic events occur over aeons. The memory of the solar system is not easily lost. In a way that fits the narrative of margins already constructed, the most catastrophic outcomes for Pluto might still leave readable artifacts. To consider the future of Pluto is to accept both the fragility and the redundancy of cosmic record-keeping. 12. Conclusion. 1. One persistent lesson folds through every reflection on Pluto. Margin and memory are entangled. The dwarf planet occupies what has always been a borderland, a place where the sun's agency wanes and the slow conservator of cold resumes the long work of preservation. That role is not inert, it is active in its own register of time. It is patient in its geological expressions and stubborn in its chemical resistances. The future of Pluto is therefore not merely a list of possible fates, stable resonance, collisional change, ejection, but a series of reframings about what it means to be archivist at the system's edge. To imagine Pluto's future is to practice a form of attention that modern life rarely cultivates, the willingness to think in centuries, to hold probabilities that unfurl over millions of years, and to accept surprises that arrive slowly. The dramas that could displace or reshape Pluto are not headline-making eruptions, but cumulative negotiations, the long tug of resonances, the rare rattle of a collision, the distant whisper of a passing star. Those are soft narratives in a human sense, but they write hard changes in ice and orbit. They remind observers that durability and vulnerability are not dualities but a spectrum. A world can be fragile in one sense and stubbornly preserving in another. There is a modest consolation in that hybrid state. If Pluto is nudged and its orbit altered, or if it is struck and its surface rewritten, the record does not simply vanish. Ice preserves in its own austere ways. Fragments continue to orbit and to testify. If Pluto becomes an interstellar traveler, it becomes an emissary bearing a fossilized chemistry across the galaxy. If it breaks, the shards remain legible to a patient reader with the right instruments. The story of the solar system. Its earliest recipes for ices and organics, its migratory dances of planets, its scars from collisions, will persist in forms that scholars of the far future could still decode. For those who listen, Pluto's long, slow seasons and patient surface are an ethic. They ask that curiosity be matched by endurance, that instrumentation be designed with timescales in mind, and that the categories humans use, planet, dwarf, archive, be flexible instruments rather than fixed verdicts. The margin refuses to be simply an end. It is a repository, a mirror, and a provocation. It asks observers to recalibrate scale, to respect processes that outlast lives, and to treat preservation not as a static status, but as an ongoing negotiation among light, cold, and motion. In the dim theater where the sun's light thins to a whisper and shadow carries memory rather than mere absence, Pluto stands as a patient keeper of time. Its future will be a story of probabilities, of resonant protection and occasional perturbation, of impacts that both destroy and reveal, of the small chance of exile and the quiet certainty of chemical persistence. The final sentence in that story is not written yet. What is certain is that the margin will continue to teach a humility that both unsettles and steadies. Smallness does not mean insignificance. Cold does not mean emptiness. And the edge, if listened to with the right patience, will continue to speak the oldest lines of the solar system's poem. A single emblem can outlive the label that once defined it. That is the quiet truth at the heart of Pluto's story. Though an institutional stamp removed the word planet from its certificate, the object itself did not become less strange, less instructive, or less symbolic. Instead, Pluto migrated from a place on a pedagogical list to a deeper function in human thought, a provocation about the limits of knowledge, a mirror for humility, and an index for the kinds of discoveries that still await at the solar system's periphery. The image that lingers is less about classification and more about threshold, a human symbol that refuses to vanish because it points to a structural feature of our inquiry. The edge is where what we know frays into what we must imagine more carefully. Culturally, the persistence of Pluto is telling. Children learned a tidy count for the planets. Adults carried mnemonic anchors shaped by that count. When institutional definitions changed, a communal memory resisted erasure not because it rejected scientific method, but because symbols perform social work. They compress narrative. An endpoint becomes a story. A figure becomes nostalgia. The sentimental reaction to reclassification was not merely a refusal of taxonomy, it was a signal of how humans use celestial maps to orient themselves. Yet the scientific reframing, the recognition of Pluto as an emissary of a populous Kuiper belt rather than a lonely terminus, expanded rather than diminished meaning. Pluto now does more cognitive. Scientifically, Pluto's meaning matured into something operational. New Horizons taught that an object's classificatory badge was subordinate to what the object could reveal about the physics of cold, the choreography of volatiles, and the record-keeping of deep time. The pale polygonal plains, the jagged water ice ranges, the layered hazes, the seasonal heartbeat of a microbar atmosphere. All these particulars turned a once remote point of light into a laboratory for questions of preservation and process. The dwarf planet came to stand for the idea that the margins are not barren, but conservative. They slow chemical turnover, trap volatiles, and shelter signatures from the thermal and biological erosion that obliterate primordial records closer. That functional status makes Pluto a symbol for scientific humility. Discoveries at the edge tend to arrive by subtraction. The careful exclusion of background, the patient accumulation of faint photons, the willingness to wait for orbital confirmations measured in human decades. The edge rewards instruments designed for slowness, surveys that sweep the sky for years, occultation networks timing dimming stars with distributed telescopes, data pipelines that let pattern recognition emerge from noise. The people and institutions that build such capabilities become custodians of patience. When discovery is measured in photons per hour and confirmations in orbits per century, the symbolic value of Pluto is not an abstraction. It is a reminder that, beyond metaphor, Pluto's persistence raises a practical and provocative question. How many other Plutos are there objects at the margins that, by virtue of distance or faintness or our conceptual blind spots, have not yet been recognized for the depth of their stories? The question has several dimensions. There are bodies of similar scale and composition that remain undetected simply because they are small and dim and their orbits place them at aphelion for centuries. There are detached objects on extreme orbits whose aphelia push into the realm where interstellar encounters and galactic tides become significant. There are dynamic populations, resonant groups, scattered disks, the inner Oort cloud that hold members too faint for even modern survey telescopes. Detectability is a technical constraint with philosophical consequence. A body at 40 or 50 astronomical units, reflecting a few percent of incident light, presents a tiny signal to telescopes on Earth. Add to that inclinations that push objects outside ecliptic focus surveys, rotational states that smear light curves, and surface properties that alter reflectance, and many objects simply evade initial discovery. But the observational landscape is changing. The next generation of wide-field surveys facilities like the Vera C. Rubin Observatory promise to scan the sky with a cadence and depth unprecedented in human history. Infrared facilities, space telescopes with sensitive detectors tuned to the thermal glow of cold bodies, and coordinated occultation. Yet instrumentation alone does not guarantee conceptual insight. The history of Pluto teaches that an object's significance is often recognized only after multiple modalities converge: astrometry to fix orbit, spectroscopy to reveal composition, occultations to reveal atmosphere and size, and finally in situ reconnaissance to resolve morphology. Each technique carries its own constraints and biases. A spectroscopy that reveals methane depends on adequate signal-to-noise and on surface illumination. Occultations require the geometry of alignment and a network capable of capturing them. Flybys demand decades-long commitments and political will. That synergy is why Pluto's story moved from discovery to meaning slowly. It required patient accumulation of different kinds of evidence. Speculation about how many Plutos await must also reckon with scale. The Kuiper Belt is enormous in number and variety. A small fraction of its members will be of Pluto's size and complexity, even among objects hundreds of kilometers across. Thermal histories and collisional pasts diverge. Some will have retained substantial volatile inventories and perhaps even the capability for transient atmospheres. Others will be rockier, shaped more by collisions than by sublimation. The further one looks, the greater the heterogeneity. The existence of Eris, Haumea, Makemake, Sedna, and many others already demonstrates that plurality. The statistical expectation is not a single dramatic twin to Pluto, but rather a spectrum, numerous worlds that, when resolved, will each alter certain assumptions about formation, migration. These expectations carry both promise and burden. The promise is obvious. Each large trans-Neptunian object is a potential archive, an icebound ledger of isotopic ratios, volatile inventories, and irradiation products. Sample a cold trap in one basin, and one might read a sequence of atmospheric epics written in frost. A cryovolcanic edifice might deliver material from depth, offering direct data about internal chemistry. The burden is temporal and logistical. Missions to these distances are expensive, require decades to develop and execute, and return data slowly. The political and cultural appetite for long-term projects is often weaker than the urgency of near-term priorities. The question of how many Plutos exist. There is also a speculative axis that is simultaneously intriguing and unsettling: the edge as the best archivist for traces of deep prehistory, natural or otherwise. Coldness preserves chemical bonds, absence of liquid water reduces microbial degradation pathways, low geologic activity leaves stratigraphy intact. Within those constraints, certain signatures, refractory mineral anomalies, unusual isotopic fractionations, durable engineered materials would persist far longer at the margins than they would closer in. This is not an evidence claim about any past technological civilizations. It is a methodological observation about preservation. If an investigator asks where the longest-lived physical records of a system might be found, practical answers point to cold, distant. The possibility of undiscovered Plutos also invites humility about the relationship between scale and significance. A small body at the margin can force major revisions in understanding simply because it preserves a different facet of history. An object that retains a pristine, volatile mixture could chart gradients in the protoplanetary disk. A collisional family can record the mechanical violence of early planetary assembly. A detached orbit can point to external perturbations that trace the sun's birth cluster, or even hint at distant massive perturbers. In other words, scientific impact is not proportional to physical size alone. The quiet, preserved archive of a modest body may, through its chemical fidelity or dynamical peculiarities, be disproportionately practically. Searching for more Pluto-like worlds requires strategic thinking in three domains. Observationally, the imperative is breadth and depth. Wide-field surveys with sufficient cadence to catch slow movers but also targeted deep fields and off-ecliptic latitudes where high-inclination objects may lurk. Occultation campaigns, distributed globally and involving both professional and amateur networks, provide opportunities to measure sizes, and atmosphere networks provide opportunities to measure sizes and atmospheres for objects too faint for direct spectral study. Infrared detection complements visible light surveys by revealing thermal signatures. Theorists must then synthesize disparate data streams, orbital distributions, spectral slopes, albedo maps into models that can infer evolutionary pathways, and prioritize must balance ambition. There are social challenges to these technical tasks. Long-duration projects require intergenerational stewardship. Instruments are designed by one cohort, launched by another, and interpreted by many. Funding models tailored to electoral cycles and short news cycles must accommodate the slow accrual of knowledge. Effective public communication is crucial. Collective patience becomes easier to sustain when narratives emphasize the cumulative nature of discovery rather than the immediacy of spectacle. Pluto's story provides a precedent in how astonishment and patience can coexist. The excitement of new horizons came after decades of quiet accumulation. And what of the question's emotional underside? The idea that many more Plutos await at the fringe carries an implication about human scale. Each new distant world reinforces that human history is a narrow filament within a much longer cosmic fabric. That realization can produce discomfort or ecstasy depending on temperament. Yet there is also consolation. The multitude of remote, preserved places means that information is not necessarily ephemeral. The solar system, in its margins, keeps copies of its own childhood. It is a vast library with many shelves still unindexed. For a species that values stories, this is a form of cosmic generosity. Finally, the question resists finality. How many other Plutos are waiting to be found is not a figure that can be nailed down from a single vantage. It is a function of observational capability, of the particularities of orbital distribution, and of the thresholds human institutions set for what constitutes discovery. The more important lesson is methodological and ethical. Treat the edge as a reserve of memory, design instruments and projects with time horizons that match the processes under study, and maintain an intellectual posture that privileges patient inference over premature closure. Pluto's symbol does not vanish because it encapsulates a persistent human orientation toward the unknown, curiosity tempered by patience, wonder tempered by discipline, and narrative appetite tempered by the humility that scale forces upon us. It functions as a mnemonic not for a count, but for an approach that sees the margins not as a dead end, but as a conservation zone where the earliest pages of a system's history are kept legible. So the question remains, open and productive. How many Plutos are still to be found at the edge? The honest answer is both simple and wide. Enough that they will modify current narratives, enough that they will demand new instruments and patience, and enough that in seeking them humanity will continue to learn how to read history written in frost. The symbol endures because it points to this ongoing task. It asks observers to listen, to wait, and to keep the light of inquiry burning at the rim where answers arrive slowly and change the view when they do.